But actually, when does this when is the sessions gonna when is the end of this session?
Oh, let me check the schedule.
In your time or our time? It should be about 3 hours last I checked.
Okay, so 3 hours from now.
Yeah, 3 hours is the plan.
5, 10, 11. So. It ends at 11 for you.
Okay.
10 for me. So yeah, welcome back everyone. We're just going to wait around for a few more minutes for people to join, and we'll be starting on the hour. I'll make a quick introduction and pass over to John, one of the showcase moderators who is hosting this final session. Okay, so welcome back everybody for day 2 and our second and final session of the weekend, Legged Robots. It's been a fantastic weekend, and stick around at the end as I talk a little bit more about plans for the Reddit robotics community for the future year. I'm now going to pass over to John, who's been one of the showcase committee team, has helped put this together, and he's going to introduce our keynote speaker and foreshadow the coming session. So John, over to you.
Thanks, Ollie. So as we all know, legged robotics is probably one of the most technically demanding control problems that we can see in the robotics field itself. With that, I proudly introduce Shamel. He is a roboticist that is broadly interested in providing robotics-oriented solutions to real-world problems. He started his education with a bachelor's in mechatronics from the German University in Cairo, currently holds a master's of science in systems and control from the University of Twente, and completed his PhD in advanced and humanoid robotics from the Italian Institute of Technology. His research has primarily been focused on robotics and control, with his doctoral research in developing terrain-aware locomotion for legged robots. This requires reasoning about the robot's surrounding environment, using its onboard perception, developing online strategies using controls, optimization, learning. Currently, he's a postdoctoral researcher at the Dynamic Leg Systems Lab at IIT, and he is currently presenting his work on HighQ. So take it away, Shamel.
Perfect. Thanks, John, and hi, everybody. Yeah, so today I'm going to be mainly talking about legged robots. I decided to divide my presentation into two parts. So the first part, I'm going to be talking about an overview of the robots that we built here at the DLS lab. And the other part of the presentation is going to be talking about how to make robots terrain aware, which was in part of my PhD that was it. So yeah, without further ado, let's start. Just maybe if you can click on this link, this is going to give you the same rendering of the presentation slides that I'm having right now. So maybe in case you have some problems with videos and stuff, just check it out. It's going to give you a better rendering for the videos. So yeah, the Dynamic Legged Systems Lab, or the DLS Lab for short, is part of IIT, which is the Italian Institute of Technology. It's in Genoa, in Italy. The Dynamic Legged Systems Lab have been around for 14 years. We're focusing on legged systems. That mainly started with the PhD of Claudio Semini, who's the head of the lab. So we're broadly interested in making robots walk, but that also requires working on robot design, control, locomotion, and perception. And the main focus is also on to make robots walk or during heavy duty operations. So the way that we envision this is that we want robots to aid human beings in several applications. Here I'm just counting some application like construction sites or planetary explorations, warehouses, package delivery, and agriculture, but also in search and rescue missions where you don't want to put humans in there. For example, think of the cases of what happened in Chernobyl or Fukushima, or even in Notre Dame in Paris. And so let me just give you an overview of the timeline of our lab. So we started off in 2008 with the first prototype of the leg of HighQ. Then we followed that up in 2011 with the first version of the HighQ platform. Then in 2013, we developed two of these HighQ robots. One of them is the one that we're currently using here at the lab. The other one went to ETH, and then like 2 years ago or so, it went to the University of Trento in Italy. Following that up, we followed with an arm on top of HighQ. So we had a HighQ Centaur, but also we developed the second generation of the HighQ flagship robots. That's HighQ 2 Max in 2015. And then we developed a mini version of the HighQ robot in 2016. 2019, we came up with the third generation of the robot, that is HighQ Wheel. And then most recently, we put an arm on top of it so that now we can also do some local manipulation. And for this talk, I'm going to be mainly focusing on these three types of robots: HighQ, HighQ 2 Max, and HighQ Wheel. So let's start right away. In here, you can see the early work of the HighQ robots. These are actually one of the first steps that the robot took back in 2008. And you can see a little bit of a sluggish performance here for these steps. The main reason was that we were doing this open loop with pre-generated trajectories at that time. And so starting that time forward, we started focusing more on low-level control. So mainly also controlling the joints, legs, and torso. And in here, you can see different applications. For example, on the top right, you can see some strategies or a recovery strategy on how to let legged robots try to recover from any push. But also you can see here pretty cool locomotion capabilities on trying to traverse through different rough terrain. And what's important to show here is that at this time, all of these locomotion capabilities that you're seeing it's a blind locomotion. So the robot doesn't see what's around it. It has no terrain awareness for it. But then with HighQ, so with HighQ, you can see here its range of motion for the leg or the workspace of the leg. You can see it's pretty small. So this was one of the challenges that we had for the HighQ robot. And that was mainly something that we wanted to fix with the second generation. And so for that, when we developed HighQ 2 Max, we took that in mind to have a broader range of space that you can, of workspace that you can see here in the green curve. And so because of this, it allowed our legged robots to do self-riding. So if it comes up, if it's in a position where that it's falling over, it can self-ride itself. And here you can see it, for example, at the left figure, how would it do the self-riding. But also it still shares the same capabilities or the same locomotion capabilities that the HighQ platforms have. And then after that, we were thinking of what does HighQ 2 Max lack? The first thing that we were thinking of is power autonomy, because as you can see here that the robot still has the hydraulic pump unit, or the pump is outside, is not on board of the robot. And you can see here also that we're connecting the power supply from not on board. And so what we really wanted to focus on was on power autonomy, which and because of that, we decided to have the hydraulic pump unit, or the HPU for short, on board also with the power supply. And also we wanted to improve the robustness and the reliability of the actuators that we have. And because of that, we teamed up with Moog, which custom designed these actuators, these hydraulic actuators for us, and using 3D titanium printed technology. And that was the third generation. That is the third generation of our flagship robots. And as I mentioned, we want to focus on robots for heavy duty operations. And because of this, we were wondering what might happen if we would put these robots to let it pull like something as massive as an airplane. And so we took the robot, we took HighQ Wheel to the airport of Genoa. And with the help of Piaggio Aerospace, we borrowed their Avanti airplane, which weighs more than 3 tons. And we decided to do some experiments to see if the robot is capable of pulling that plane. This is part of the video that was in 2019. It went viral in 2019, showing HighQ being able to successfully pull that airplane. I mean, that day was a great day for me personally, because I've never seen something like that happen, and it was truly inspiring to see it like a real time robot pulling it like that. But of course, before pulling the plane, we had many experiments. So this, for example, is showing you the first steps that we had for HighQ Wheel. This was the first time we would try everything and see what would the robot do. But also, since we were pulling a plane, we decided, okay, let's try to compete first against ourselves. So here you can see Michele Focchi, who's one of the postdocs here, the researchers at the lab, trying to push against HighQ. And when that was successful, sorry, Mickey, we went over with that. So we wanted to pull a car this time. So we took Victor Balaswols, who's also a researcher at the lab. He took his car. I was the one actually inside that car, and I was pulling the handbrakes halfway through. And yeah, going back to the part of the workspace, now HighQ and HighQ Wheel and HighQ 2 Max have also a larger workspace that allows us not just to do these kind of stuff and also different locomotion, but also it allows us to traverse, it allows the robot to traverse through confined spaces, which is also really important for the applications that we're thinking of. Now, this part this is one of the projects that we're working on recently. The first version of it, or the first part of it, got concluded in 2021. It's about Tele Manipulation with HighQ Wheel. And so we teamed up, or a couple of labs of IIT teamed up with INAIL. INAIL is the National Institute for Insurance Against Accidents at Work here at Italy. And what they want is that they want to separate humans from hazardous situations. So we were trying to look up for ways that we can move workers from these situations, that they can put in a safe environment and let robots work in these dangerous situations. And that made us think of teleoperation and on teleoperating the robot. So what the main purpose of the project was to teleoperate the robot. So you would have an exoskeleton, a hand exoskeleton with a virtual reality interface that we refer to as a pilot station. And the pilot station is then going to be teleoperating the robot that has an arm on top that can do similar, that can do different kinds of local manipulation. This is a quick overview of the Tele Manipulation or of the system that we're having. So on the left here, you can see the field robot, which is HighQ integrated with a custom designed arm for such application. And on the right here, you can see the pilot station, which has the hand exoskeletons with an arm and the virtual reality interface. Let me give you a little bit of information about the arm. So the arm, as I mentioned, is custom designed here at IIT to fit the project requirements. It has 5 DOFs and it weighs 5 kilograms if you're excluding the end effector. Also, it can carry up to 5 kilograms. The controls there is using torque control or impedance control. And here we optimize the space to do some different things. So for example, like configurations for picking up or for normal operation, but also to have it in a stow position so that it can distribute its weight on the robot. And the hand that we're using here is called the HERI hand, which is a 4-fingered hand that has an integrated pressure sensing and visual feedback. So this is just a video to show you what the hand can do, what the exoskeleton can do. Here you can see it, for example, doing some manipulation, so picking up some objects transparently. So you have the hand being like the robot is a KUKA robot, then just picking this in a teleoperative way. And here we have the arm with the hands and also the teleoperative exoskeleton. This was at Maker Faire. That was before COVID. I can't remember exactly when this was happening. But here you can see, for example, how to pick up a tennis ball on top of a bottle. And here we were showing Enrico Mingo trying to catch that ball. And this is the integration of everything. So what we want to show here is the robot being teleoperated. For example, here we wanted to break the window and to take the hose. So here you can see, for example, what the pilot is actually seeing. It's only seeing these 2 cameras from the VR. Here we're showing another example when we wanted the robot to just open a door. And again, in the bottom videos, this is what you can only see within the pilot station. Here we're showing some other things, for example, like how to pick up, like showing the robot picking up some objects and putting it back for inspection, for example. Yeah, so that concludes a brief overview of the HighQ robots, or the robots that we have here. I'm not gonna go through this table. I think it's just cool for you if you would go back and check it out maybe later in the offline version to see the comparison of the different platforms. And then here they're without the arms, so they're the actual robots. So this actually takes us to the second part of today's talk, which is about terrain awareness. So this is the same video that I showed you in the beginning when I was talking about HighQ in 2013. This video also went viral alongside other quadruped robot. I think at that time, Big Dog from Boston Dynamics was also doing some pretty cool locomotion. And as I was just mentioning, that ever since then, this was blind locomotion, but ever since then, the goal was to let legged robots or move legged robots away from research lab into the real world. And so if we go back to these applications, and if we want to bring legged robots to the real world, thinking of these applications and wondering if there's actually anything in common in all of these applications. And to me, the first thing that is obvious here, that's in common at least, is that the terrains that the robot traverse are never the same. Matter of fact, like the terrain that the robot is traversing, they could be dynamic, means that they can move. They're not stationary. They constantly change. It's also unexplored. Like if the robot has not traversed this place before, or you don't have any map prior on that. But also the terrain itself could be uncertain. What I mean by that is that the robot can be in situations where you do not get certain information from the terrain, like in scenarios where vision is denied, or if the robot's perception is noisy. And so the take-home message here is that the terrain itself introduced a large amount of uncertainty. And the way to deal with this is to let legged robots terrain aware. So the solution is for legged robots to be terrain aware. And if you're not familiar with the term, terrain aware locomotion means that the robot is able to take decisions based on the surrounding terrain using its perception. So just abstractly speaking, the main idea is that you want the robot to perceive the surroundings, so perceive what's around it. And then using that, it can start to reason or understand it and understand the information that it's perceiving and reason about it and take decisions based on that. So this is me, like I wanna categorize terrain aware locomotion into two categories. The first category is called proprioceptive terrain aware locomotion, or PTAL for short. And the second one is exteroceptive TAL. So with PTAL, PTAL strategies are strategies that rely on the internal robot measurements to acquire the terrain information. ETAL, on the other side, rely on directly acquiring the terrain information, mainly using the robot's vision. So for example, PTAL strategies are gonna be relying on the internal sensors of the robot, like load cells, torque sensors, encoders, etc. But exteroceptive is not only, of course, vision. So it's not only LiDAR or radar or cameras, but also like temperature sensors, for example. Let me give you a couple of examples of proprioceptive terrain aware strategies or PTAL strategies. For example, on the left here, you can see an early work of our lab in 2013 by Fahmi et al. And the idea here is devising what's called reflex strategies. And basically what happens is that the robot here tries to use its internal sensors or its internal measurements to detect if it collided with an obstacle. And then if it collides with an obstacle and detected that, it can adapt its swinging trajectory fast enough so that the robot doesn't fall. And on the right here, you can see a work that is done in 2019 by Baraswal et al., which they're also doing kind of something similar, which is to detect if there's an obstacle or not. But not just that, the key here is to also detect where on the leg, to localize where on the leg did the robot collide with an obstacle, so that later on it can adapt its trajectory based on that. Now going to ETAL strategies or exteroceptive strategies that mainly use robots' vision. Here I'm showing you two videos of the robot trying to perceive the terrain information and trying to select what would be the best foothold that the robot can take in order to safely traverse these obstacles. I'm going to be talking a bit in detail about these two strategies later on, so stay tuned for that. But now that we have talked about PTAL strategies and ETAL strategies, when would you use that and when wouldn't you not? So PTAL strategies are important when visual feedback is denied, like in areas that are smoky or areas with thick vegetation, for example. But also if the terrain map itself is unreliable, you might want to use PTAL strategies. However, PTAL strategies, based on their nature, they are limited to corrective actions. What I mean by that is that if you took a look at the reflex strategies that I was talking about, the robot first had to collide to detect that it's in contact. So what I mean is that they don't act on what is ahead of the robot. And so if we go back now to the goal about terrain aware locomotion, which is to let legged robots take decisions based on the surrounding terrain using their perception. We can define three main keywords here: decisions, terrain, and perception. So the decisions could be at the control level, at the state estimation level, or at the planning level. The terrain itself may vary in its frictional properties, in its physical properties, like its friction or impedance, or in its geometry. And the perception here is either using the robot's proprioception or using its own vision. And so for the rest of today's talk, I'm going to be talking mainly about three types of terrain-aware locomotion strategies. The first one is about whole body control in general, which is a terrain-aware locomotion strategies that act as at the control level to adapt to the robot's friction and geometry, to the terrain's friction properties and geometry, using the robot's proprioception. Then I'm going to talk a little bit more in details over locomotion over soft terrain. So how to make the robot adapt to soft terrain. And this is at the control level and the state estimation level. And lastly, I'm going to be talking about VITAL, which is the most recent work on vision-based planning. So it's a vision-based strategy at the planning level to adapt to the terrain's geometry using the robot's vision. And in these three strategies, I'm going to be using optimization and machine learning as tools. And we're going to be, we're going to validate these strategies, or we validated these strategies on the HighQ and the HighQ Wheel platform. So let's start with these strategies. But just maybe before that, I can give you some pointers in case you wanted to check these work later on. So the first part about the whole body control is published at RAL. Stance, which is the part of soft terrain, is in TRO. And the work of Vital currently, we're planning to submit it, but you can see it or you can get more information in my PhD dissertation. So about whole body control. Now, if you want to achieve dynamic locomotion, or if you want to have breakthroughs in legged robots, the robot should be able to track the trajectories that you give it. That's obvious, but it should also try to maintain balance, so not to fall down. It should also be able to reason about its own dynamics and its own limitations. But also, if you want it to be terrain aware, the robot should also not just reason about itself, but it should reason about about the contact or about the terrain. So, for example, like the terrain's inclination or the terrain's physical properties. And so if you want to deal with all these objectives in an optimal way, the solution is to devise a whole body control framework. So let me tell you a bit about the whole body control framework that we're using here at the lab. So the whole body control framework starts with the locomotion planner. And the idea of the locomotion planner is that it spits out trajectories for the legs and for the base. And then we have a state estimator module that feeds back the states or estimates and feeds back the states of the robot. And then using the planner and using the state estimator, the whole body control is going to realize the trajectories from the planner, taking into account the limitations that I just explained. And then it's going to spit out optimal torques that are going to be sent at the low level to the low level controller that is going to be then sending the torques to the robot. Let me briefly tell you about the objectives of the whole body controller. So as I just mentioned, we want to execute the planned trajectories. So we want to realize the planned trajectories from the planner, but also we want to keep the robot balanced. We also want to respect the unactivated part of the dynamics, as well as the activated part and the joint limits. We want to respect the contact constraints that I mentioned. So we want to be be aware of the terrain. So the first thing that we want to do is that we want to enforce or encode friction constraints, which basically enforces the robot not to slip. We also want, for example, since you're walking on a ground, the ground is never going to push towards it. It can only it cannot push, not pull. And then we also want to maintain contact consistency. And what I mean by maintaining contact consistency is that, for example, if you are in a rigid terrain and the robot is standing still, you want to enforce that the standing legs, the stance legs don't move. So you want to enforce it to be stationary. We refer to that as the stance task. And now that we have all of these objectives, what we're going to do is that we're going to cast them as an optimization problem and solve it via quadratic programming. And then we're going to map the solution from the QP to optimal joint torques using inverse dynamics. So these are just a couple of results to show you what the whole body controller can do. Here, for example, you can see that the whole body controller is capable of tracking the motion and adapting to different terrain, rough terrain conditions, such as, for example, different terrain inclinations, but also under different gates. You can also see, for example, at the bottom video that the robot can also maintain balance even if it reaches or if it stands in a foothold that is unstable, like what you can see here, for example, when the rock was moving away. So just to recap, the passive whole body controller, or the whole body controller that I mentioned, is aware of the terrain's geometry and friction. It can also achieve dynamic locomotion and at the same time compliantly balancing the robot's trunk. And we showed how it works under different gates and different terrain conditions. And now the question would be, can you still say that that whole body controller is terrain aware? And the answer to that is not really, because of soft terrain, for example. So if you take a look at that whole body controller, but also other locomotion control strategies in general, they most of the time assume rigid contacts, which is good. It's not bad actually, because it keeps our equations and formulation a bit simpler. So it's easy to use. But at the same time, if you take a look at the world around us, nothing is always rigid. Things are not just rigid. Things are also stiff. They're soft at the same time. So this is actually a problem, that most of the whole body controllers are not terrain aware, meaning that they fail to generalize beyond rigid terrain. That's the first issue. The second issue comes from soft terrain itself. I mean, think of or imagine yourself just jumping in front on a flat terrain or a rigid terrain and jumping on a trampoline, for example. You can see that soft terrain on its own induces contact dynamics. And so with these two together, that becomes a serious issue, because there's going to be a mismatch between what the whole body controller assumes, as you can see here, for example, in blue, versus what's actually happening, that the robot is walking or is walking on a compliant ground. So how do you think we can solve this? The first thing that we can do is that we can drop the assumption of the rigid terrain. So use a more general or a general model that can take into account not just rigid or stiff terrain, but also different terrain impedance. But then that's not enough, because how do you know the impedance parameter of the terrain? You're going to be walking through so many terrains. How are you going to know that? And the answer to that is to simply just estimate it. So this is how this is how how to do that. We have the standard whole body controller that I explained, and as I just mentioned, we're going to reformulate that to be compliant contact consistent. And what I mean by compliant contact consistent is to be consistent to different compliances of the terrain. But as I also mentioned, now that whole body controller, for it to be compliant contact consistent, it needs the terrain impedance parameters. And so because of that, we have a terrain compliance estimator module that is going to measure the terrain, or is going to estimate the terrain's impedance based on the robot's measurements, current measurements. And we're going to do that at every control loop. So the terrain compliance estimator is going to estimate what terrain impedance is the robot traversing, is going to send it to the whole body controller that can take that into account, send it back to the robot, and so on and so forth. And we refer to that approach as STANCE, which stands for soft terrain adaptation and compliance estimation. So let me show you what can STANCE do. Here, for example, I'm showing you in simulation at the top and experiment at the bottom, what can STANCE do, which is what you can see here is that you can see HighQ being able to traverse multiple terrains with different compliances. Here, for example, in the experiment, you can see going from soft to rigid terrain, and even transitioning between that. And here we wanted to see what kind of cases would any of the approaches, that the standard whole body controller or the new approach, which is STANCE, if any of the cases would fail. And so here we did two types of simulation. The first one on the left here is called a speed test, where we let the robot walk while continuously increasing the speed up until one approach, or if any approach fails. And on the right here, we show what would we show aggressive trunk maneuvers. And in these two cases, we can see that STANCE was able to accomplish the task, while the standard whole body controller did not do that. And the main reason behind that is because of the compliant contact consistency of STANCE. STANCE understands what kind of terrain it's walking over, and so because of that, it tries to come up with optimal ground reaction forces, for example, or optimal trajectories for the robot to take. Here, for example, you can see the difference, or some cases in simulation, in experiment. You can see, for example, that since STANCE is compliant contact consistent, it can generate consistent compliant contact forces that, for example, you can see here at the left is going to result in less shakes, for example, for the robot. And in the table here, you can see the mean absolute tracking error in the ground reaction forces. And you can see that STANCE is indeed outperforming the standard whole body controller in that case. Here, I'm just showing you just two different experiments. For example, on the left here, we're showing that STANCE also works not just for slower gates, but also at more, or using more dynamic gates, such as the trot gate, for example. And on the right, we see the capabilities of the terrain compliance estimator to estimate different terrain impedance parameters. And as you can see here, we used 4 different terrains, and we showed that the terrain compliance estimator of stance can indeed independently sense the compliance under each leg. So just to recap that with stance, unlike the other standard whole body controller, we do not assume that the ground is rigid anymore. And because of this, we're able to adapt to any terrain compliance online. And also because of this, HighQ was able to traverse and transition between multiple terrains with different compliances without any p-tuning. We also showed that stance is, again, compliant, contact consistent. This allowed HighQ to remain consistent with the ground, and thus it was more reliable or more robust in challenging scenarios. So this brings us to the last part of this talk, which is about Vital. So just to give you a little bit of context, I'm going to be talking about locomotion planning, or vision-based locomotion planning in particular. And locomotion planning strategies can be divided into 2 things: coupled planning and decoupled planning. So coupled planning, the idea is that you're going to plan the feet and the base states simultaneously at the same time. So you're going to have one module that is going to spit out these references. But with decoupled planning, you separate the plan. So you have a planner for the feet and a planner for the base. I'm going to be focused about decoupled planning. So today I'm going to be talking about decoupled planning. And so if you want to plan the feet motion, we refer to that by foothold selection. And if you want to plan the body motion, we refer to that by pose adaptation. And let's talk mainly about foothold selection first. So with foothold selection, the goal is that you want the robot to select the best foothold based on the terrain information that it perceives, but also its capabilities, its own capabilities. I'm going to be explaining in a while what are the robot capabilities, but I wanted to show you here 3 different examples to that, or actually this is our work on foothold selection. It started in 2015, where the idea is that we wanted to teach the robot what would be the best foothold that it can take. So because of this, we relied on expert demonstrations. So the expert or the user was the one teaching the robot or labeling the data to the robot, what is the best foothold and what is not, based on the inputs that it gets. And in 2019, Villarreal et al. Have improved on that. So he has improved, or the work has improved the kind of criteria or the kind of capabilities that the robot has. But also now, to teach the robot, we did not rely on labeling the data that we had, but we were using self-supervised learning, and we trained it via neural networks or convolutional neural networks in that case. And then in 2020, Esteban et al. Improved on the versions of 2015 and 2019, and also they improved the structure and the architecture of the CNNs that we were using. And we refer to this work as the vision-based foothold adaptation, or the VFA for short. Now that we have talked about foothold selection, there is one issue though, or one problem that one can see, is that despite the work on foothold selection, pose adaptation strategies lag behind. So why is that a problem? If you think of it, if you want to select what would be the optimal foothold, basically the leg just can't move on its own. You have to also move the pose of the robot. And so if you want to do foothold, in general planning, foothold selection and pose adaptation, both of them are important, because you cannot remove them from themselves. They move simultaneously with each other. For the leg to move, also the pose has to move. And this is the importance of pose optimization. So these are a couple of related works on pose optimization. And the goal of the pose optimizer is to adapt the robot's pose similar to the foothold selection. The foothold selection was interested in adapting or finding the best foothold based on the terrain information and the capabilities, or what the robot can do. With pose adaptation is the same, but for the pose now. So we want to adapt the robot pose, so using the terrain information and what the robot can do. But there's a problem with the current pose adaptation techniques. And the problem is that these strategies, they focus on finding an optimal solution based on given selected footholds. What I mean by that is that the pose adaptation relies that first footholds are selected. And once you select these footholds, you optimize the pose on top of that, okay? So first you select and then you optimize. But there's an issue in here, because what would happen if this foothold if the robot did not reach this? For example, if the robot gets disturbed, what would happen to the pose of the robot? The answer is that the robot might end in a position or in a pose with no safe footholds. The robot is in a state that there are no safe footholds around it. And so in order to solve this, we propose a different paradigm now. So instead of finding footholds or optimizing the pose based on given footholds, we don't want to do that. We want to optimize or want to find the body pose that is going to maximize the chances of the robot to reach safe footholds in the first place. So we're not just optimizing with respect to given footholds, but in general around the robot. And so we want to put the robot in a state that if it gets disturbed, it's going to remain around a set of solutions that are still safe and reachable. And we refer to that work as the VITAL, which stands for Vision-Based Terrain-Aware Locomotion. So VITAL is a vision-based decoupled locomotion planning strategy. VITAL has three main modules or three main blocks. The first block is called the VFA, which is the vision-based foothold adaptation that I just mentioned. It's an improved version of it. So it's the VFA that is going to select the foothold based on the robot skills. But also there's another block that is called vision-based pose adaptation, VPA. And the VPA here is the pose adaptation strategy, but now it maximizes the chances of succeeding in reaching footholds in general. And I keep on talking about capabilities, safety, success. All of that notion comes from skills or emerge from skills. And these skills are things that we teach the robot that explains or characterizes the robot's capabilities. We refer to that by foothold evaluation criteria, or FEC for short. So now, what do I mean by capabilities, or what do I mean by skills? So in here, we're teaching the robot how to avoid edges and corners. So how to select footholds, for example, that is not gonna be at the edge or at the corner, or how to select footholds that are gonna remain within the workspace of the robot, or how to avoid colliding with the terrain. All of these are skills. All of these are capabilities. You can know more about this either in my dissertation or in the references that I mentioned. But let's now talk about how the VFA works. So the VFA, what the VFA works is that first we extract what we call a height map, and the height map is just a small subset or a small region in the terrain map, in the actual map that the robot sees. And using this height map, we're going to evaluate what would be the best foothold for the robot based on the capabilities that I just mentioned. Once you know what is the optimal foothold, you can then send it and adapt the trajectory of the robot. Now, the thing is that the foothold evaluation on its own is usually computationally expensive. And so what we do is that we rely on CNNs, or we rely on neural networks to approximate the foothold evaluation so that then we can run it online on the robot real time. Similar to that, also with the VPA for the pose adaptation part, you're going to extract height maps. You're going to evaluate for each leg, for example, what is the best height that it can take that is going to result in the maximum number of safe footholds based on the capabilities of the robot. And then you're going to have a pose optimizer on top that is going to optimize and find the best pose that can satisfy or can maximize the safe footholds for all of the feet combined. And again, since the pose evaluation or evaluating the robot's capabilities is computationally expensive, we rely also on CNNs here. It's a different architecture though, of course. So let me show you what can VITAL do. Here I'm showing you the capabilities of VITAL in crossing stairs. So using the VPA for pose adaptation and using VFA for foothold selection. And here you can see that we had here 4 simulations going from 0.2 meters per second up until 0.5 meters per second using the HighQ robot. And then we also tested that on the HighQ Wheel platform. Also from 0.2 to 0.5, climbing stairs using the VFA and the VPA But what's important here to mention is that HighQ Wheel, as I explained, has larger workspace. So traversing this kind of stairs was a little bit relatively doable compared to HighQ Wheel. And because of this, we wanted to go higher than that. So we decided, we also simulated HighQ Wheel at a faster commanded velocity of a 0.75 crossing these stairs. Now, this is actually, I think that's super cool because HighQ Wheel is more than 130 kilograms. And so for a 130 kilogram legged system, walking at 0.75 meters per second, that was super cool in my opinion. Now, these are just super early preliminary experiments for Vital. We're trying to test it on the real platform. But this is currently something that we're currently working on trying to transfer the strategies from simulation to the real world. So just as a recap on Vital, we showed that Vital allowed HighQ and HighQ Wheel to traverse wider variety of terrains. I just showed you stairs here, but in the dissertation, in the thesis, or also hopefully soon for the work of Vital, you can see also different kinds of terrains like gaps and also different types of terrain. And we showed the importance of the VPA, the pose adaptation part, that it's going to result in body poses that are aware of the terrain and also what the robots can do. And this is the end of the part of Vital and my talk in general. Now, I wanna thank all of course, the work that I mentioned about terrain-aware locomotion is not only my work. I would like to thank all of my co-authors for that and for their great help throughout my stay at IIT. But also, I just talked about one part of our research in the lab. But there are other different kind of research that we also do, including MPC, for example, feasible region or state estimation. And also there's a really cool research that we're doing on how to make quadrupeds walk or balance quadrupeds for using 2 legs only. That concludes my presentation. I hope you enjoyed it. And I would like to also thank the partners that we've been having working with the DLS lab. Here are just some pointers to the DLS lab. You can visit the website if you need any more information. And of course, if you need anything, just try to reach me out wherever you want through social media. So that's pretty much it. Thanks all.
Awesome. Thank you so much, Shamel. So we have a few questions that are on the YouTube chat right now.
Okay.
I'm just going to go in order here. So first is, what materials and components are you using for the arm, actually, that you talked about earlier, that keeps it at a 5 kilogram mass?
Good question. Easy answer, I don't know. I would highly recommend you to check the paper. There's an aim, the paper pretty much talks about everything about the arm. So where is it? Let me just go through it. Yeah, it's this one, a compliant mechanism with the progressive stiffness.
So
I know that some parts are 3D. Most of it is printed in at IIT, but some of it is also just plastic. And just check the paper. I think it's better if you would do that.
Okay. So the next one, and this is actually one that I'm a little interested in also, is that since you are using ML approaches, how are you exactly accounting for like robustness and I guess generalization? Since earlier you had mentioned that, you know, when we are on like terrain that legged locomotion is really good, you know, it's often dynamic, unpredictable, and therefore, you know, what we learn now is probably not going to be useful later. So how do you account for all of that?
That's a really good question. Let me try to first reach through that, but even not, forget it. So yeah, of course, generalization is a huge issue that we find, but also there are many techniques. So for example, the way we learn our neural networks, let me go here, for example, for the VFA, is that the inputs to the VFA are height maps and other robot inputs. So basically we sample these height maps. You can, if this height map is just a matrix, so you can literally sample all of the possible combinations of the matrix. So you can get pretty much, you can go through that generalization from playing or tweaking with the data. That's one thing. Another thing is that we also try to inject some noise into the data so that we can make the neural nets more reliable. One thing that is also important that we don't just we focus on finding tools. So we don't just focus on the implementation using neural nets, but we also try to be a little bit smart when we devise the locomotion strategies. So for example, we know that the neural network is not going to be super perfect. It's not going to be 100% accurate. We also know that the states of the robot are not going to be accurate. And so in the foothold evaluation itself, we have different modules that account for uncertainty. Simple thing, for example, is that if you choose a foothold, you want to make sure that whatever is around it is also safe based on the evaluation that you get. So for example, if there's a little bit of a drift in the state estimation or a problem in the accuracy of the neural network, then you can take that into account already. Did that answer your question?
I think so.
Okay. I just want to pop in real quickly. Thank you. Great presentation, by the way.
Thanks.
I know I've had a lot of people in the comments asking to check out some of the links and the resources. Just to let you know, I'll be following up with a lot of the participants, and we will have a Reddit post as well shared to Discord, which will have a lot of the resources that people have mentioned in their presentations after.
Yeah, perfect. You know what? Actually, we can have an AMA for that. Truly,
we can put something together. And yes, in that post, you'll be able to ask some of these people questions. They're Reddit users. They might pop up and answer it. There's no guarantee, but that will be something that happens. Next question, because I know there's a lot, so I don't want to intrude.
That's all right.
Yeah, no problem, Ollie. So next question is, and it comes from Nathan, how do you see learning coming into locomotion and the manipulation problem? Should they consider the whole body, just the arm, or just the leg? Any particular thoughts on that?
Okay, so first of all, let me answer the last question first. Just the arm or the whole body. I think if you can have any strategy that can spit out the whole body states of the robot, that would be cool, because then you would be reasoning about everything in the meanwhile. That's not in the meantime, simultaneously. So it's not just for learning techniques, it's for learning, optimization, or anything. That would be cool. The thing is that up to now, it's not really feasible. So we try to work around. And that's the main idea of decoupled planning, that you can have two different modules that can be a little bit tractable, and you can have a bit more control over its computation. But for example, something cool about Vital is that even though it's not whole body in a sense that an optimizer or a learning strategy spits out the robot states, the feet and the base states, so the whole states. In Vital, things are decoupled, yes, but they share the same skills. So we have a foothold selection module, a Pos Adaptation module. Both of them are working not in the same optimization problem or learning problem, whatever, but they share the same skills. That's the first part regarding the second question. Now, the first question about learning, I mean, I try to not think first if I should be using learning or optimization or controls or whatever. I try to see what tools do I need. For example, a cool example is the VPA. We knew that the post-evaluation part is hard to compute, and that's why we used learning for that. But we also wanted to have an optimization that can enforce constraints, that even whatever output you're going to get from the neural network, you're still going to have constraints over, or you can have control over. That's why we're using both of them at the same time. But I do think that learning is really important, and I do think that people should be trying out different learning strategies. I think there's a lot of things to try in locomotion that is still yet to come, actually.
Awesome. It's really insightful, actually.
Thanks.
So next question is are these newer motion planning strategies more computationally complex? I think you touched on that a little bit in the presentation, but does introducing stance and vital planning pose a greater challenge for real-time planning?
Okay, that's also a good question. Let's first separate between stance and vital. Stance is pretty, I mean, stance, both of them are real time, but stance, I think it's less computationally expensive. I mean, running QPs in our platforms is not something, it's not in 2021. I mean, people have been using QPs for a long time, and it's pretty efficient, and it's real time as well. Stance has a state estimation module that was still running real time. You can definitely control. You would have a trade-off between how fast do you want an update from the terrain versus how accurate that information would be. But I would just comment saying on stance that I did not really have problems with real-time issues regarding that, especially also that really the terrain compliance part. So the learning part was pretty like the model was explicit. You can solve an analytical solution, so it's not a hard it's not computationally expensive for the robot. That's using stance. Now for sure, for if you want to estimate the terrain compliance using a more complex model, then this is something that we should start talking about computation issues. Now regarding Vital, it really depends. Evaluating evaluating the robot capabilities is computationally expensive because you have a height map, you have a matrix, for example, and you want to check each and every pixel in that matrix. You want to compare it to using different modules. So that's when computational burden comes in. But again, that's what would be a great example for using neural networks in that case. I hope that answers the question.
Oh, I think so. I'm actually going to build on that a little bit. Okay. So I've noticed with each version of the HighQ robot, it seems like each leg has just 3 degrees of freedom. If we extended it and like adding an ankle to each one of the legs, and therefore grew the degrees of freedom for each leg, how do you see the actual growth and expansion of Vital playing out with that? Like, is it going to wind up exploding in complexity as a result of that? Is it going to just kind of keep the same because you're just pruning the neural network and locking it down to what its architecture is?
Yeah, so that's really cool. So of course, when you the entire idea of Vital is based on the robot skills. So even if you add an ankle, or not just that, if you want to add another skill in general for the robot, that is of course going to increase the computation of the full evaluation offline. If you train the neural network, of course it might change the computation because you might be playing with the architecture of the neural net. So yes, it's going to increase. I don't think it's going that the computational complexity is going to increase proportional or linear to the skills, because actually something that is really cool that we're using here for the skills, for example, is that you can evaluate one skill that is already gonna kick out many footholds already. So then you use the other skill that is gonna cancel some footholds. So I don't think that adding a new skill is going to be linear or proportional to the computation complexity is going to be proportional to that.
Okay.
But for example, if you think of a whole body controller, yes, because I mean, the decision variables are going to increase. That for a whole body controller or for any optimal controller, really, any controller really that uses optimization, the decision variables, you're just going to augment them. So if you have an arm, for example, not just an ankle, you're going to increase the decision variables. So you're going to increase the computation as well. Yeah, I think so.
Awesome. All right. And then I'm just trying to double check. I think there's one more question.
Okay.
Okay. So the question here is, in general, I'm really curious. We see now Boston Dynamics dog robot and others from China and this robot. We're seeing, for example, Intel versus AMD like competition among all of these technologies. What will become the standard for legged robotics?
That's a really hard question to know. But I mean, the way I see legged robots now is that still in terms of design, it's not saturated yet. There's a lot of things to be working on now in locomotion, in control, in high level. in terms of having a standard for legged robots, is there even a standard for manipulators, really? I don't know. But I think in general that now legged robots is a bit in an earlier stage compared to manipulators, for example. So you still see people working on improving the technology of the platform itself. So the robot designs, like the DLS lab, for example, and other labs and even other companies. So I don't think really there's a standard. I don't know, correct me if I'm wrong. Maybe I didn't understand what you mean fully by standard.
Yeah,
Comment a
I
little
generally
on
agree
this.
with you too. And I often remember the XKCD comic of, we have 15 competing standards. Let's make one to unify them all. Now we have 16 competing standards.
Yeah.
That same point was brought up yesterday by someone as well.
Yeah.
Can I ask a quick question as well? Well, we have a few minutes as well still before the next
Sure.
one. So does HighQ Wheel use hydraulics?
Yeah, good question. So all of our robots use hydraulics.
Right. Okay.
HighQ means hydraulically activated.
Yeah. Okay.
So,
so my question then is, I've seen that the Boston Dynamics, yours, and a lot of these bigger robots are using hydraulics. Do you think that there is a cutoff point at which robots are large enough and they have to be built using hydraulics and they cannot be built with using electric motors? Or do you think that the technology for electric motors will catch up? Or, why is it that, is there a pattern here, a commonality, or is this more of a design choice? Do you think this is something that is based around size and weight?
Okay, so first of all, I think, and I'm talking as chairman, not as the DLS lab. I think working on hydraulics in general, or hydraulics control, is cool because it's hard. It's harder than electric actuation. And trust me when I say this, it is hard. It's hard to control. The technology is not as advanced as electric motors, for example. But that's why we work on it in the first place. Now, I think only really everything depends on the application that you want, right? Like if you want to pull something really heavy or you want to operate in heavy duties, electric actuation did not reach that point for having this power, and that's why people use hydraulics. But at the same time, hydraulics is, as I told you, it's hard. So you don't always need to use it in every single application, right? That's a good thing of having different, diverse types of robot, not a standard robot.
Yeah, I think that feeds back into the last question of saying, yes, we're building different robots for different intended applications.
Exactly.
Your robot isn't going to be something that you're going to buy as a pet to keep in the house anytime soon.
Yeah, as you just said, anytime soon. Yeah, pretty much. I mean, now, for example, no, it's going to be hard to have it as a pet. The technology, as I told you, is not really advanced yet. And informally, if you think of it, that's maybe why Boston Dynamics stopped using hydraulics for spot, right? Because if you want to put that in more of indoors or as pets or stuff like that, no, it's not pretty advanced yet compared to electric actuations, for example. But also, you can see how important hydraulics is by still keeping Atlas with hydraulic actuation, right? So at the end of the day, really, it depends on what application and what you want the robot to do. That's what's important.
So you wouldn't see hydraulics as the superior, the correct answer. You'd see that, even when hydraulics becomes optimized and great, it's still not going to be the dominant form, and electric motors are still going to have their place in lots of robotics.
I think I don't know. But I know that there's nothing more superior than the other. It really matters on the application. Now you can say maybe one is better than the other because it has more applications. Okay, but in my point of view, in my opinion, I think it really matters on the kind of application that you want these robots to operate in. There are cases where you want electric robots. There are cases where you would want hydraulic robots. It really matters on the application.
Okay, wonderful. I'll pass back to John now.
Okay.
Thanks, Ollie. So with that, actually, I think now it's time for us to introduce our next presenter. So Piotr is going to be demonstrating the Wolfie Quadruped. Let you take it away from there.
Hi, hello.
Hello.
Let me just share my screen. Okay, can you see it?
Yep, you're good to go.
Can you see the screen?
Yes, we can.
Great. So hello, once again. My name is Piotrek Wasilewski. I'm from Poland, and today I'd like to tell you something more about my recent project called Wolfie the Quadruped. Thanks for having me, to the organizers, and let's head to the details. So basically, I wanted to create a robot that would be an ambitious task, and basically it would be a platform for me to learn new things. I wanted to create a robot that would be small and relatively cheap, but at the same quite agile. So I didn't want to go for the servo-based solutions because they are usually quite slow and you cannot really implement force-based algorithms on them. And you cannot implement the compliancy that is inherently connected with animals and humans. So that's why I created my own modular brushless actuators to enable that. And yeah, as I mentioned, the robot is really small. It isn't obvious from the render, but the outline of the robot, when you look at it from the top, is the dimensions of a A4 paper sheet. So only 210 by 300 millimeters. I started by designing the actuators.
Just want to show folks that's a 300 millimeter ruler there. So that's the size.
Sorry?
That's a 30 centimeter ruler. So you said 300 millimeters length.
Yeah, exactly. Mm-hmm. So it's quite small. It isn't always obvious from the renders or the photos. So that's why I mentioned it. Yeah, so I wanted the actuators to have the high speed and high torque capability. That's why I implemented it based on the brushless motor. The module that I've created is able to produce 3 Newton meters of peak torque at 30 amps of phase current and 875 millinewton meters of continuous torque when it's thermally limited. So when it has a certain temperature that it cannot exceed, the controller commands some kind of throttling to reduce the temperature of the actuator. Each model weighs around 210 grams and has a 4.5 to 1 gear ratio. So it is very easily backdrivable. You can easily move it from the side of the output so that it enables me to actually measure the reaction torque acting on the actuator output based solely on the motor currents. Which is quite useful when you want to estimate the force, the reaction force that is applied to the foot of the robot. So you don't have to go for the external sensors placed in the foot itself. In the exploded view, you can see the parts, the individual parts, but I think it's quite obvious. The question that I get asked a lot is what's the origin of the gear set itself? So my answer is just the electric drill gearboxes. So basically I extracted the gears for the modules, and the motor itself is a off-the-shelf one, but it's quite severely modified. Okay, so now a few words about the controllers. They are located behind the motor, right behind the motor. And they had to be designed from the ground up because they had to be really small. In this case, 32 by 32 millimeters. You can power them from up to 24 volts and they can supply up to 30 amps of phase current. What is important to not mistake these controllers with ESCs that can be found in drones or RC planes, because they are pretty different. In this case, we want to precisely control the torque of the motor. That's why we go for the field-oriented control that has these measurements of rotor angle and currents, as can be seen in the diagram below. And this basically allows us to precisely control the torque in a very wide range of speeds. So not only we can command torques at non-zero speeds, but also we can command full torque when the motor is stalled. The last thing I want to mention is the FDCAN communication bus that is used to both receive and send commands from and to the main command unit. It's like a faster version of normal CAN bus. So after completing the first prototype, I built this test stand with 2 linear rails. And as you can see, I 3D printed the leg prototype with 3 actuators and performed these repetitive jumping motions to ensure that the actuators are durable enough and they meet the performance that I need. And basically, the mechanical structure was rigid enough, and it survived over 1,000 jumps. The only thing that actually broke was the foot that was too soft to handle the contact with the wooden ground. And after checking the performance of these 3 actuators, I proceeded with making 9 more of them. And on the left-hand side, you can see the amount of aluminum stock that went into making these parts. So over 5 kilograms of these aluminum slices that I faced milled on both sides. And then each individual part was milled from these prepared stock parts. It took me around 30 hours of milling to get the total of 72 custom parts, so 6 per actuator. And now a little bit about the torso itself. So there are a few PCBs inside. There's a power board that distributes the power supply from the battery to the actuators. And it has also a small pre-charge unit that slowly ramps up the voltage so that we don't get this high current spike when instantaneously turning on the voltage for the actuators, because each actuator is equipped with high capacitance on the DC bus. So it could damage the connectors or the switch in case when it's turned on instantaneously. There are also 2 power and FDCAN distribution boards. And as the name suggests, these are only connector boards that are connected in parallel to distribute the communication and power supply buses to the actuators located in the 2 parts of the torso. There's also the control board that is equipped with 2 microcontrollers. One is responsible for translating the SPI commands from the Raspberry Pi to the actuators. So it acts like a converter between SPI bus and FDCAN bus. And the other one is taking care of the IMU and wireless communication, as well as some diagnostics of the voltage and current consumption of the whole robot. So basically a few measurements from the battery itself. The battery is located...
You've got about 2 minutes left.
Okay, I'll try to wrap up. The battery is located in the lower deck of the robot, so 8 cells, 18650 cells connected in 4 series 2 parallel fashion. There's also a BMS, as you can see on the right-hand side, the real-life assembly of the battery. Yeah, so I think this is pretty much about the battery. And here are some photos of the real-life assembly. The first one on the left shows the 3D printed structure of the torso and 4 actuators that move the hip. Then there are the tie actuators mounted to the hip actuators and cables routed through the body to the inside of the torso. And on the last one, you can see the mechanically completed robot. However, as you can see, it lacks a few PCBs. And here's a live, maybe not live, a recorded demo of the full body kinematics. This is a comparison between the simulation conducted in PyBullet and a real robot that is controlled from the Python script, the same Python script that controls the simulation. So it performs 3 translations in all 3 axes and rotations as well. And I think that's all from me now. So thank you very much. And if you have any questions, feel free to ask. You can also find me on Instagram, blog post, and Hackaday. Thank you.
Okay, hi. Can I just clarify?
Mm-hmm.
You don't have to answer this question because it's a personal information. How old are you?
I'm 23.
Okay, so you're 23. You've designed the actuators yourself.
Yes, yes.
And you've done the motor controllers yourself.
Yes.
And you've done the body design yourself.
Yeah.
And the physics simulation yourself.
You've
implemented it in PyBullet.
Sorry?
You've implemented your model of your robot in PyBullet to simulate.
Yes, yes, but it's just the simple demo. So the hard part was were the actuators and the whole structure, let's say. So
wow.
Thank you.
Wow, dude. Wow. That's an incredible achievement. That's absolutely incredible. Okay, let's go to the questions. But wow, absolutely. And some people are asking, yeah, open source it. Anything you share with this, the world will want to know about. So you should set up a GitHub, and you should make sure that you've got some email contacts that companies can start wanting to hire you for this as well.
All right.
Right, I'll pass you on to John for the questions.
Thank you.
I completely second everything Ollie said as well. In fact, I find it interesting because throughout your presentation, a lot of folks have been heaping praise actually on this. And I have to admit, it is absolutely amazing to see what you've put together.
Thank you.
That said, so other than the first question of please make it open source, I think, yep, actually we got one other question. So what was your budget for the project itself?
It's hard to tell because the project is like, I don't know, almost 2 years old, I think. So this was like, distributed along the way. But yeah, I had to check the bill of materials to give you the exact amount. But as I said, it is quite hard to estimate because it was quite a long project and some things have changed during the development. So it's not that easy.
Could you give a rough price? Is this between 500 and 1,000 euros?
So if I had to estimate the price of one actuator, because I think the actuators are the most expensive parts of this robot, so I'd say it's like $300 per actuator. But again, it's hard to tell because the parts, the custom milled parts, were milled on my machine. So I don't know what's the prices in the like professional companies that use the CNC milling machines to get these parts. So yeah, it's quite hard to tell.
Okay. So we do have one other question. I apologize for not actually seeing it first and going straight to what the budget was. But the question is we were able to see that the controller uses an STM32. Did you write the firmware for that from scratch? And then could you also give an overview of some of the challenges you faced doing so? Additionally, why did you select that specific STM32? And how did you handle it with the global chip shortage?
Yeah, I think the shortage is affecting us all. So I don't have a way to deal with it other than asking my friends that do electronics for, sourcing a few parts for me too. But I chose the STM32G4 because it is optimized for the motor control tasks. Oh yeah, it's here. It has like a core DQ unit for trigonometric calculations, and yeah, some features that allow it to run the algorithm faster. So, and it is quite common in the modern controllers. So yeah, that was like a obvious choice. And if I have to tell about the challenges, I think there were quite a few, because the controllers in my case have some history. I think I tried to make a controller for 3.5 years now, and I failed at first, but now it's quite, let's say it works. It has the bootloader, so I have an easy way of upgrading the software when these actuators are actually mounted to the robot itself. And yeah, I think the challenges that I faced were the maths related, so tuning the controllers.
Sorry, we're at the time limit. We're going to have to move on to the next presentation, I'm afraid.
All right. Okay. Yeah, so I think I've covered pretty much.
Okay. Well, thank you again, Pi.
Thank you very much.
All right. So next up, we're introducing Robotallic, the micro robot using smart materials, presented by Haider.
Right. Let me just share my screen. Second. Okay. Can see everything?
Yes, we can.
All right, cool. All right, hi everyone. My name is Haider, and I will be talking about Robotallic today. So yeah, start right away. All right, so today, this presentation was designed just to be as simple as possible and as general as possible, so that all audience can really grasp an idea on what's Robotallic. We'll start with introduction, what's Robotallic in general, and then we'll see problem statements so that we know why we need small robots. We'll go then for a small description about Piotrek strip, and then we'll go a little bit deeper in Robotallic and how it's made, the history. And then straight away, we'll jump into demo and then Q&A. Right. So introducing Robotallic. Robotallic simply is a small robot that uses smart materials as actuators. And these smart materials should be very available so that anyone just can buy out of the shelf. Because we have now really a lot of different smart materials out there in the market, but then I was interested in how can I integrate this stuff in a small robots. Robotallic was actually driven from bimetallic and robot to make this name a little bit interesting. So now the problem here, we can see the man here on the right. Yeah, you can see the man here on the right trying to, with a camera, trying to look into a collapsed building and see if there is any survival to save. And on the left, we can see fire ants nest that you might want to study. So both of these cases, you really cannot use bigger robots to actually do the job. In details here, this is another just a picture we see people trying to, in a rescue operation, which is in a very small space where large robots cannot really fit in there. And this is just a fire ant nest. For example, you want to study them up close for a long duration of time and really live among them so that you can really see all the behaviors and all that stuff. And that's why we have small robots, and that's why Robotallic is here. It's great because it can fit simply in a small places. Bimetallic strip is just simply two metals, which they have different coefficients when they stretch if they're heated. They're simply just attached to each other, and then when you heat them, one of them will stretch more than the other, and it will bend, as you can see here. This is a small demo from Physics Demos channel that we can see.
So I'm heating on both sides to convince you that I'm not cheating by just heating one side and having it expand. So that is a bimetallic strip.
Yeah, so simple. So we have such materials, but now we have small robots. And in small robots, as we can see here, it's all started in 2016. I actually was seeing all these amazing robots made by people. And at the same time, I was fascinated by small insects, really, like how small it is and how it walks. These motors that it has to really make it locomote from one place to another. And then the question was really, do I have to really build a very small motors to make a very small robot? But the answer was no, obviously. So I started to look into smart materials. This is not actually the first project that I have done to really try to move something really small. But in particular, this Robotallic, it started just with a 50-cent coin attached to a muscle, which I call right now. And the concept there worked great. So I moved on next to simply make two-legged robot so that I can test the concept in 2016 as well. Things worked okay. 2019 moved to prove the concept further by building four-legged robot. But then it uses only 4 muscles so that I can prove the concept. It worked great. The fourth one, Robotallic in 2021, this year, obviously was made for this event, especially. I started to make a prototype with a very different type of muscles. It's the same thing, but a different shape, because different shape will give you different responses. And yeah, that was simply it. This is all the dimensions that you need for this robot. You can see that later on Pos if you're interested to go when you're on. I can also source all the files and everything later on. Yeah. So some of the specs, this robot is really small. It's just 3.5 centimeter by 2 centimeter by 2.8 centimeter for this version. And in each version, everything might change. The robot is currently weighs only 4 grams without all the wires and everything else. It's just plain the robot. It has a speed of 1.75 centimeter per minute. It's not fast, which I hope things will get better in the future. And for now, it uses 2 amps at 15 volts per muscle. Here's some rendering for the robot. The new version uses now 8 muscles, and it's a little bit better in terms of how it was made, because now it can be made really fast, and for any modification and testing. I'll jump right here now to demo. In this demo, I will let my old self who made this video to speak here a little bit and show you just how it works.
Walking. Basically, there's a couple of ways to move the robot, either by using the upper muscles only or using the lower muscles only. The best that I have found so far is to make them all work together in a sequence, as we can see here. However, there is 2 types. There is the short stretches, which will make the robot walk in a smooth surface. It will make it walk faster, and it will be like hopping. Like this save you see here, for example. The robot is normally controlled by the best prototyping tool in history, Arduino, and 8 relay module. There is also 2 power supplies, one for the relay module and the other one for the robot. For best functionality to the robot, it uses 2 amps of current at 15 volt as a minimum supply. A higher current was used when more than 1 muscle is activated, but it kept like at 4 amps.
So yeah, this was basically how it walks. Of course,
basically,
yeah, this version have, as you listened before, short stretches, and this is the longer stretches. What it means is when you heat it more, the material will flex more, and thus you have a longer stretch. but it will be slower as well, as we can see here. It obviously can go backwards as well just by reversing the algorithm, or we can make it go forward. This is simply just the Robotallic current version. Yeah, so I'm still in a point. I'm actually now answering a question. So where is the good starting point for this? Because as you said, you have seen like it uses 4 amps at 15 volts, which is really high, which I'm hoping in the future to find a good shape for the muscles itself, so that it can be low power and at the same time perform better. Yeah, you can find more info in my YouTube channel, Mechanical Cell, or in my website, which is Mechanical Cell Space. This is basically it, and I'm open for any Q&A. Anyhow.
Thank you so much. So we do have one question, and I'm actually gonna kind of keep on to this a little bit. So the statement is that the author supposes that a big issue would be containing heat transfer, since any heat radiated from, like, let's say, power, other electronics, might actually affect just everything at that small scale and cause unwanted actuation. Additionally to that, I would even ask, what considerations would you have for just ambient temperature effects as well? So if we were to deploy this in, like, let's say, like the middle of the Serengeti, where, we have a temperature difference like night and day about like 15 C. What would you say about that?
That's a great question, because when I was building this prototype this time, I looked into the different composition of these materials. Now, you have really different types. There is types that hardly gonna be affected by heat, like too much, let's say, and it's really like a margin of error that I had to count for when building this robot, even now for this version as well, and to make sure that the heat will not gonna affect like the different muscles in the robot itself. For now, for example, I'm using PCBs. Obviously, just milling them with the CNC machine so that I can make sure that the heat transfer will not gonna affect other muscle. So yeah, it's really just depends on the type of the material that you're using. That's all.
Okay.
The effect, yeah. The solution that one can use.
Okay. Next question is it some specific lengths of limbs that contain the bimetallic strips, or is it actually the whole limb as you're developing it?
What, you mean the material itself?
Yeah. So, like, for example, with one robot that you had shown, we could see that there was one strip that seemed to come out of the circuit board into basically a knee joint, and then another strip of other material that went to the foot. Are they the same materials, or are they different? Are they contiguous?
You mean, for example, here the upper muscle,
Yes.
The W shape, for example.
Mm-hmm.
They're not connected. It's not one limb. That's why you have a knee joint here between the two different muscles, so that you can actually control them individually. But here the shape, it's actually, I'm still trying different shapes. The reason why the upper muscle is actually wiggly like this is to make it longer, because with a longer material you can stretch more, and thus you can have a very long stretch for the leg. Mm-hmm. So yeah, that's how it is.
Okay. Next question is how do the legs hold up with repeated heating and cooling cycles? Do you have any problems with wearing out or with fractures associated with that material?
Actually, there's none of these problems, but other problems, which you will notice when the robot walks for a long period of times, the muscles start to really compress, become smaller and smaller, and the stretches become smaller and smaller. I have thought of this problem before, And the solution that I'm trying to find now is actually how to make them flex faster so that they can cool faster, and then how to really make a cooling system for each muscle. And this is a thing that I have to really develop for the next prototype that I'm going to build and tackle this problem.
Out of curiosity, do you need to be able to cool each muscle at different times, or do you just have to be able to cool all of them?
As of cooling, you have to cool the one that you have run. Like, for example, if I turn on the upper muscle and then switch it off, the best way is to cool it. If you can notice here, you can see there is magnets. And these magnets, it's actually their plates so that it will help to push the leg to its original position so that I can heat it up again and make it flex. So cooling is absolutely necessary.
And yes, but if you added a larger surface area to the metal, how would that affect it? Because that would increase its cooling, but then that would also affect its ability to work as a muscle, would it?
Actually, no. If I can cool the muscle itself faster, if I can just cool it, it will be better. Because one of these problems with this robot is that actually you have the control of one thing. Is you're gonna heat the smart material, it will flex, and then it will go back to its original position. So you have only control of one direction if you wanna. I'm
not being funny here, but have you tried running it in a fridge?
No, I haven't tried that, but I have tried to run it underwater.
Okay, wow. Okay, so there was me thinking the question. Underwater, how did that work?
Actually, Ollie, I'm sorry about this, but I think we need to move on to our next presenter.
All right. Sorry.
But that's really interesting, and I hope we can follow up on Reddit right afterwards. So,
I want to see a video of it underwater, please.
All right.
Okay. So thank you again. That said, so I'd like to introduce Kevin Chow and his attempt at converting a toy into an autonomous robot.
Hi guys, can you see me?
Yes, I can.
Okay, cool. So hi, I'm Kevin, and this is the robot that I made. You'll see that shortly after I go through my presentation. So I'm gonna just screen share real fast. Right, presentation mode. All right, so yeah, so my thing's just converting a toy into an autonomous robot, a legged toy specifically. It's called the Hexapod. By the way, there is my LinkedIn and my Reddit in case you guys want to look me up later on. So this is still a work in progress. So there's still like a bunch to be done. So, just a bit of warning. And as for legged robots in general, so for many legged robots, you would need multiple motors to control each joint. You might have one motor for the lower leg, one motor for to control the upper leg, and so on for each leg. And for these robots, you usually have to figure out how to control each motor individually to get them into position that you want them in order to walk. So that would either you would have to do something involving lots of math or stuff like that, or find code that someone else already written that already does this. But then alternative for that is, having a fixed structure, fixed movement in which the legs are, they're arranged in a way so that when you, have a motor that rotates them, they move in a fixed walking pattern, as is the case for the lower left here, which is clamp linkage, and the bottom right here, which is Jensen linkage. Both of these are, structures that, have fixed movement. So as for what I, worked with, it's Hexapod Spider XL, which is a kid's toy that's remote controlled. And despite being called a spider, it only has 6 legs. And the way it works is that, like, you know, you have 4 backward movement and turning of its head that controls which direction it moves in or faces. And in total, there's actually only 2 motors, one for a forward backward motion and one for the turning of the head to change direction. So that essentially reduces, like, you know, having to deal with many motors to figure out like how those motors would need to go in order to walk, to having to deal with only just 2 motors. And my goal with this is, you know, I just want to see how advanced I can make just like a simple toy become by just adding a bunch of stuff onto it. And as for the stuff I used, there's actually a bunch, not going to include the stuff like, you know, just tape, wires, and, you know, other somewhat basic stuff. So I started with a Hexapod spider, which I actually got for cheap from some random guy on eBay. And then some zip ties, some switches, some screws, nuts, standoffs, stackable headers for like the Raspberry Pi that I used, some battery holders, SD cards, also 2 different RealSense cameras. And I used a motor controller hat, a fan for cooling down Raspberry Pi. Of course, Raspberry Pi itself, it's a Raspberry Pi 4 8GB RAM version. And I also like 3D printed some stuff. This was essentially the 3D printer that I used. And I also have these extra things. One HDMI plug that's, you know, just for, I guess, mainly debugging purposes, so I can like easily remote into my Raspberry Pi easier. And also a Pi Juice hat, which is essentially provides power to the Raspberry Pi. And also, you know, like a set of batteries as well for controlling or powering the motor controller itself. And all this comes to around a bit over $1,000. Some of the cost might be like, you know, lower if I had made better like choices of like not buying bulk of some stuff. As for software itself, I used, you know, I put on my Raspberry Pi Ubuntu Mate 20.04 to 64-bit version. And on that has ROS Noetic and Python for some of the code that I've written for controlling motors. And as for like the my first iteration that I posted on Reddit, it's basically looks something like this. And this was before I got like an upgraded you know, battery for you know, the Pi Juice that is powering the Raspberry Pi. So you know, the reason why I have this power bank here in this first iteration is because like apparently the cameras, like, they draw a lot of power. Yeah, and I eventually, like, you know, upgraded the battery to this one. You kind of see right there that, like, you know, reduces the need to have that extra power bank. And yeah, and basically there were some problems that I initially faced, and I guess somewhat currently face as well. Like sometimes is that there's a lot of stuff that I stacked onto the robot. So there's some issues with the weight. And like the robot wobbling and falling over a lot. So if you guys ever played, like, you know, the game Death Stranding, like, you know how like you might end up having to have a bunch of stuff on your back and you're constantly like tripping and falling. That's like what I kind of experienced like a lot of times, like especially with the whole camera setup and extra batteries and stuff. And another issue is that the robot inherently doesn't walk straight. So that is something I haven't got around to dealing with, but like I just left it for now. And then third problem is that the Raspberry Pi is like, while it's simple to use and stuff, it's not exactly entirely that powerful for handling, like, I guess a lot of the software that the RealSense cameras will use. So a bit about the RealSense cameras actually is that the reason why I have two is that, like, initially I wanted one camera to deal with the depth sensing and all that stuff. And then the second camera is mainly for providing, odometry and tracking, like, the how fast the robot will essentially go. So yeah, and I guess now I can get to like a live demo of robot. Right. Just disconnect my robot from charging first. Set robot down on the floor. I'm gonna switch my camera to my other camera that should be pointing towards the floor.
There we go. Camera switch worked.
Yeah, just make sure you can see. Yeah, let me just all right, so just flip this, and I'm gonna just launch some stuff from my end.
John, I don't know about you, I'm so excited right now.
Yeah, it's running some stuff. Yeah, I'm just like I haven't exactly organized my code necessarily so that it launches in a launch file. I'm just like running stuff individually right now. So
don't worry, that's common.
Yeah. Okay, and maybe I should actually maybe tell you guys what you should be seeing like later on after I start this last script is that I'm essentially going to be kind of doing like a simple obstacle avoidance somewhat where obstacle avoidance meaning like when it sees a thing in front of it that is too close, it will turn to the left until it's not looking at the too close object anymore. And yeah, just a simple thing.
Okay. So we're meant to stop at 1:45, but we have a coffee break after that, and I think everyone is more than happy to stick around an extra few minutes if you're about to give a demonstration. So we will happily give you. Oh, there it goes.
There it goes.
And yeah, I guess I'm just holding this box in front of it.
That is so cool.
Yep.
So there are a few comments, and I was a little curious about it myself. I know that it's very top heavy. Have you invested anything into maybe trying to give it a stronger sense of balance to at least give it better motor control so it doesn't fall over as much?
Yeah, like so I haven't actually like implemented any balance control or anything yet, but I guess I had some like ideas that so one thing is that the RealSense camera, the one that has the depth sensing capabilities, supposedly it has an IMU that maybe I might be able to like utilize to maybe you know,
You have very
maybe
limited
detect
control
when
of
there's
the
about to fall or things like that. Whether that will actually work or not on a Raspberry Pi, I am not too sure about. It's something I have to experiment with to find out.
You might want to consider upgrading from a Pi to a Jetson Nano.
Yeah.
When we saw this application, we absolutely loved it because of its comically top-heavy nature and the video of it walking around and managing just step right is
it's like, you know, I basically took like you know, a
see.
spider and just made it look more like a, you know, a lasagna with legs.
Yesterday we had a robot that was a lawn flamingo that had been turned into an animatronic, and a lot of people were saying that should be the mascot for the subreddit. I'd like to suggest that we take a photo of this one and put those two up against each other and have a vote to see what we want to make to have replaced the Boston Dynamics robot, because I absolutely love it. It's great in that it's both very hacky in using a toy, but also there's a lot of very creative and very, you know, talented work that's gone into making that top-heavy stack functional and doing what it's capable of doing. So it really is a great mascot in that sense for the robotics community. Well done.
Yeah.
So if I could also ask Kevin, I mean, I myself, I started out my robotics career just like you, like trying to hack things apart, trying to put it together because I could. But as I progressed through my career, I've learned a bunch of lessons learned from that. And I'm actually very curious about what lessons you've learned from this too, like from going with that approach of starting with a simple toy and then trying to build on top of that. So.
Yeah, like I guess like a lot of like the things I learned from this is mainly, you know, what kind of works and what doesn't. It's like you know, I guess mainly when you try to put a lot of stuff like on top of a little wobbly thing, it gets more wobbly. I mean, that I guess that should sound obvious, but like, you know, initially it actually had more stuff on it, and it's like the cameras were a bit more forward, so like it kept falling and stuff. So it's like mainly just a lot of you know, working with mechanical like design issues, I suppose. And
well, would you take that starting mechanical design of that toy and maybe redesign it yourself? Or
I think like the great thing about this is that, like, you know, it kind of serves as a somewhat a prototyping like platform for like you know, potential like you know, future like upgrade to like a maybe a more advanced like walking robot, like potentially. Yeah.
Awesome.
Yeah, I think, you know, if you have a 3D printer, then your next step could be looking into, there's so many open source Hexapod robots out there, which just servo motors, and you wouldn't even have to worry about the electronics because you've already got that stuff taken care of. And it would just be a bigger, more powerful flat platform that's a bit more stable, and it gives you individual control of, you know, 6 legs if you wanted. So that could be something to consider in the future. Either way, I look forward to seeing what work you come up with in the future.
Me too.
Yep.
Well, thank you so much, Kevin. I'm looking on the chat right now. I can tell you there is a lot of praise actually for your project, but it doesn't seem like, oh, nope, there is one question actually that I'm looking at here, or two, in fact. Oh, wait, no, I was misreading that. I'm so sorry about that. So my mistake. But that said, no, thank you so much again, Kevin. With that, let's take a little bit of a coffee break and we'll pick up at 4 p.m. Hey, Robin. Are you there?
Hey.
Hey, did you want to present yourself, or do you want me to play a video for you?
You can play my video if you. I prefer that, and I'm only here if any questions afterwards. All right.
Yeah, right. You beat me to the punch. I was about to clarify that myself. Yes, we're going to play the video, John.
Okay. All right. Actually, Ollie, if I could ask, because the video that I pulled up seems to be the 16-second one. Which one should I be using?
I'll find it and send it to you.
Okay.
Hi, Robin. I'm immensely sorry, but I have lost the link to the video. Are you able to send that across quickly?
Yeah, sure.
My sincere apologies. That's my mistake.
Is it?
Ollie, we already,
is
Ollie,
it
we
Chris?
have it.
You have it. Okay.
Yeah,
The
we're
Vimeo
good.
link.
Okay.
John has it.
The Vimeo one.
Vimeo, no.
The drive one.
Drive one.
Yeah.
Okay. I have
a long one.
13 minutes, 32 seconds.
Yeah, that seems right.
Okay, right, wonderful. Sorry about the palaver there.
No worries.
Don't bring up your camera. Let's go with this.
Okay.
All right. Well, that said, time now is 4 o'clock. So I think we should start getting ready for this then. So for our next presentation, this is the Kelso Quadruped developed by Robin Fröjd. Pardon my broken English and everything. I'm really bad with pronunciation, but this robot itself was inspired by the MIT Cheetah and is roughly half the size, or well, roughly halfway between the MIT Cheetah Mini and the MIT Cheetah 3, with mass being approximately 18 kilograms. That said, we are going to present a video and go from there. Okay. There we go.
There doesn't appear to be any audio. John?
Yes?
There does not appear to be any audio.
That is strange. I have audio on my side here.
Unless it's just me, is anyone else hearing it?
No, you have to enable the share audio on Zoom.
There we go. Sorry about that. All right. I'll just start it from the beginning then.
Hey guys, thanks for letting me present my work here today. So my name is Robin, and I've been working on a quadruped robot for some months now, named Chow. It's very similar to the mini Cheetah or the Cheetah 3.
John, I'm getting really bad audio from
I
you.
started this project purely on a hobby level because the fan of it.
Pause it.
I'm doing it on my spare time. Yeah, that's about it.
John, pause the video.
It's roughly 600 millimeters long.
Okay, this is not
The Wolfie height will be roughly 35 to 40 centimeters.
Send the link to me, please.
There we go. There you go. You should have it on the chat in Zoom right now.
You also need to share audio.
Are we good? It is open.
I'm not getting audio from you, but you have to share.
Present my work here today. So my name is Robin.
Very good.
Yeah.
Working on a quadruped robot for some months now, named Kelso.
Turn it up though.
It's very similar to the mini Cheetah or the Cheetah 3. I started this project purely on a hobby level because of the fun of it. I'm doing it on my spare time. Yeah, that's about it. And here's the body. It's roughly 600 millimeters long. And the estimated walking height will be roughly 35 to 40 centimeters high. Here is a picture of the robot when I started to assemble it. The inspiration for this robot is coming from some weirdest robots still already out there today. So we have the Cheetah, mini Cheetah is the hip and body. We have the upper leg is coming from the Cheetah 3. The lower foot and the lower leg and the foot is coming from the BD spot. And the form factor is quite similar to some like a GoPro. The body is milled out of the aluminium 775. The motors is the Humars AK-109, which is roughly 800 grams each. So a huge weight of the robots is actually the motors. Here is the legs. The link length on my design is 280 each, lower and upper. Before ordering stuff and finalizing the design, I compared the different specs from a few selected robots out there. I checked the mini Cheetah, the Cheetah 3, and the Leica GoPro and compared them, and I came up with my specs and my design. So here's two sets of legs. So the first one was the aluminium 775, and I also made a set of milled carbon fiber legs. Here is a close-up picture of the carbon fiber legs. You can see the fiber structure here. Leg weights. So The aluminium legs, all legs on the robot is roughly 3 kilos, and the carbon fiber legs is roughly 2 kilos. So each part made out of carbon fiber is reducing the weight roughly 30% for each part, making me save around 1 kilos in total weight compared to aluminium. Here's just a picture of the robot on the stand. We did some testing for the motion on the motors, with the connection, the cables, the frequency. We have them running here and not on the robot. Here is some impact bars we made for protecting the robot in case of it, if it falls down, they should take the first punch, maybe save some parts. Here is other few parts. So here we have the foots. We have 3 different sets. We have 35, 40, and 45 A-shore. At the moment we are testing with 35 A-shore, and we will see in the end what we will end up with. In the middle here you have the resting cushions molded out of rubber. It's for the robot resting position. Here is mount for the cameras, the becks and the fan inlet. Bottom side, a plate for SSD is mounted, and also a spot for RTK GPS for centimeter precision outdoors. These 2 is for mounting the covers on the robot. Here is a sheet metal part, which is made out of aluminium. In the middle here we have the battery compartment. On the upside we have the up extreme and the place for a Jetson annex as well. Let's see what's happening now. Here you have some other parts. Here you have the battery inside of the sheet metal part, and on the side here you have the PJ board from MG-Bots. You have the up extreme and the vision kit mounted on the other sheet metal part, and this slot is for the Jetson annex. All the QMRC motors is running the MG-Bots controller. The stock controller did not work out as expected, so we swapped to the MG-Bots controller, which works great. Here is a folded picture of the robot. This is how small it can get if you fold it together, if in case of travel or something like that. Here is a custom milled chain tensioner. We went with a chain as a drivetrain since we wanted to reduce any chance of slippage. We wanted splittable linkage, and also we wanted the ability to change the gear ratio on the knee quite easy. So, and that's the chain allows us to do that. Some downsides maybe is the backlash. I haven't noticed any major backlash when doing testing. I think we had roughly 1.2 millimeters at the end, and that's also including the backlash from the motors. Here is the robot in a walking stand. So this stand we will use for when we're testing the first walks, also other motions, etc. Here's another stand. This stand is used at my office for testing various stuff and also to have a place for it. Here is a video of the first payload testing. In this video we are using 10 kilos on top. The total power consumption is then roughly 2.35 amps. We also did some testing with 3 kilos and 6 kilos, and you have the power consumption here. We will do more testing with that in the future. For the covers, we are going to manufacture them in carbon fiber. I find a great guy on Instagram which makes sweet stuff. I contacted him and he's making my covers. We have a picture of the 2 first covers here. They're made with 3 layers carbon fiber. Each is have a weight of roughly 125 grams, and they're very durable. So it's quite good if we have an impact or something, they will probably last. So here is a video of the first test stand of Kelso. Total weight is 17 kilos. The voltage is running is 36 volt, and the stand consumption is 1 amp. So quite good numbers for the first test stand. We will do more testing with power consumption in the future. Here is a video of the joint feedback, just simulation in over ROS in RVs. So here we have RVs running in the background, and we just doing different motion with the leg and simulate that in RVs. So before making any final decision of the design, we made a rough robot model, and we put the Chia controller on that, and we tested that in PyBullet. And here you can see all the graphs for each joint and the effort they are consuming for each step. I think the knee joint is one of the which consumes the most, roughly 25 Newton meters. So here is a picture of the electronics on board. We have the up extreme here. On the up extreme, we have a vision kit. We also have 3 PCAN cards. Each have 4 FT channels. So this robot has a total of 12 FT channels. And the first, here is a picture of the FT cards. Mini PCI, and the M2 slots. So 12 channels in total of this robot. The first test we did was just reading and sending a bit of data from the controllers, and we hit roughly 5 kilohertz on every joint on 12 channels. The CPU consumption is still not anywhere alarming. You can see it here when running 12 channels. The up extreme is also running a real-time kernel. It's not an official kernel. I made it myself. So if you're interested in that, you can see the steps here. Here is the latest plot of the real-time kernel running on the up extreme. The controller, we started out testing a Nintendo Switch for use of to control the robot. The Nintendo Switch is running Ubuntu, and we are running ROS on it. In this video, we are streaming 2 wheel-sense cameras. We are also running the Shamel ROS package, and the Joy-Con is working, etc. So for future work, we'll also look for other alternatives. I think this year we will have a bunch of different handheld gaming controllers, which will have joysticks and with better performance than the Switch, but also at a higher price point. For the vision, we have real-sense cameras. We have 2 real-sense cameras in front, the D455. On the side, we have the D435. We just tested this outside in ROS. We made a point cloud of the cameras. In this setup, we are using 3 cameras. We have 2 cameras running in front and 1 side camera. And as you can see, the overlap is quite good, and the field of view is also quite alright. Let me fast forward to that. Here you have an estimated field of view for 4 cameras, 2 front cameras, and 2 side cameras. We still have a dark spot on the back, which will be, we will mount a sensor there as well, but we haven't decided what. I think it will be a T435 or a T265. We will see. Not sure, but yeah. So for the point cloud on the cameras, looks quite right. They are still running stock configuration. We have not played anything with that. So Sorry. Now, back to that. So for future work, we will focus on making the robot walk. We will look at ROS2, etc. So it's mostly software parts left for this project. We have some more parts going to manufacture. Basically, the front head and back covers. We have a new bracket for a possible robot arm on the top, and we will see. And here is a picture of me and the robot together. And thanks for watching, guys. And a special thanks to the companies and the persons that helps me out with this. Thank you. Goodbye.
Okay. Right, that was a great video. Apologies about the technical difficulties there. We did.
No worries. No worries.
So one thing I'll say quickly before we get to the many questions, I'm sure, is that I think you and Piotrek of the Wolfie Quadruped ought to get together and have a chat at some point.
We are in the same Discord group, so we have talked before.
Well, that is not too surprising then. And I yearn to build a quadruped so I can join that magic Discord group too. Okay, on to the questions, John.
Sure. So, Robin, the first question that the audience would like to ask you is, I feel like the carbon fiber limb membranes are good in terms of strength and flexibility. Does it justify the cost and the amount of work than CNC milled aluminum limbs? Excuse me. What key points do you see with using carbon fiber?
So the cost of manufacturing carbon fiber is basically 30% higher than 75 aluminium, so not that bad, but also 30% lighter. And but I'm not thinking about the money in this project. So, but yeah. That's basically why, but I wanted them as light as possible. I think a carbon fiber is exotic, quite cool material. I like it overall. I think it's a cool look.
Okay. So the next question is, what techniques are you exploring for locomotion?
So at the moment we are converted to ROS2. We will use Robot Gym, it's called, from Nick Russo. We will try that out in the coming weeks. And that's the Robot Gym is basically based on the Google Agile imitation MPC controller. So, but that's for future work. I haven't tried that yet, but that's the plan.
Okay. So next question is what was wrong with the RMD controllers?
From the T-mute motors, what was not wrong? Basically, I don't actually remember it. I ended them up just, I just removed them because I was so tired and going back and forth with the motors was not running correctly. So it was something wrong with them that I couldn't fix. So I didn't spend any time investigating what was wrong with them.
Okay. So a question I actually have for you is, I mean, drawing from Boston Dynamics for inspiration, and I mean, even just as you've described, like different limbs, different body structures were inspired by different products that they've had. Have you looked at like others as well? I mean, we've talked about all day about a bunch of different folks kind of developing their own quadrupeds. Have you been exploring just adding other inspiration for different designs?
Yeah, I looked at the Deep Robotics a bit. Their quadruped robots. Ended up not using anything from them, but the the form factor is also quite similar to the, I don't remember what the name is, but yeah, I haven't looked around quite a lot on different robots, but only for inspiration. So everything is I draw by myself. So yeah.
Okay. Next question is did you focus on that shown arm on top, or I'm assuming what they mean by that is are you considering adding an arm to it, like the cheetah bots?
Yeah. I'm in that Kickstarter, so I will get that arm in October. So we will see what I will do with it, but maybe have it on the robot, maybe I do some other fun stuff. But yeah, I'm in that Kickstarter. Yeah.
All right. One additional question is what would you say is the greatest challenge that you've had with such an ambitious project?
I think we haven't started with that yet, and that's the software side.
Okay.
For the rest, it's not that challenging. It's just the design and some we do some. Yeah, I don't know. For the design, I think I do it for a hobby. I think it's fun. I spend all my nights in front of Fusion or other CAD software. So purely, I'm more into designing stuff than controlling them.
Okay. A few folks are actually asking if Kelso is going to be open sourced as well. I know you have put a few posts on Hackaday, but wasn't sure if you were doing like open source architecture, open source design with that.
I think so, maybe in the end, but maybe I don't see any point because there are quite a few ready robots to buy, and this will be more expensive than to buy a ready one. So I'm not sure. Maybe in the end I will do it. Yes.
Yeah, I mean, like just speaking for myself, I mean, I would even say, you know, go ahead with that, even if it is something that potentially does have a high cost BOM associated with it, simply because, you know, other folks are going to come in and possibly find ways to actually make it a little cheaper. I mean, yeah. The key thing is like, you know, this is all still very much prototypical work. You're not getting into like design for manufacturing just yet. So. But even then, it's getting other folks to kind of help contribute, might even help move it in that direction.
Yeah, of course. We will see. I'm open for opening it up, but not at this point. I want something that could actually work first.
Okay. So we've got time for 2 more questions here. The first one is how was your experience with Modus so far?
Great. Nothing to complain. Worked out of the box. Would recommend them every day.
Okay. And then last question is any tips for ready robots?
No, I don't know. That depends on the price tag, I guess. But
can I just clarify a couple of things quickly? Was Modus the mode controllers?
Yeah, MG bots.
How do you spell that?
MG bots.
MG bots.
Yeah.
TS. MG bots controllers. Okay, I've been compiling a long list of these controllers that we're vetting, and if that's your recommendation, then that will be added to the list for certain. You said you don't want to open source the robot as a whole. Understandable. What about maybe the model of it so that people could then use it? Motius, MJ bots, thank you. What about opening the model up so that people could then use it in simulation? So then people who are considering using your robot in the future could get their hands on it in some parts earlier on.
I have already opened it up for some guys I know, so they have the model. We are working together a bit, but in the end, as I said, at this stage, I will not share it publicly, but I will share if people want to join or contribute to the stage I am at now. So I will not make any changes and requests and other stuff like that. So I will keep the focus to get it ready. then we can open it up.
If you're good enough, you can reach out, but otherwise, wait for it to be ready.
Yep.
All right. I think we have time maybe for one other question. So this person's asking, any tips on PID calibration specifically with the Modius controllers?
He has a lot of good videos on YouTube, so I would recommend to watch those videos.
Okay. Awesome.
Yep.
Well, thank you so much, Robin.
Yeah, welcome.
All right. So moving along, next up we have Sparky the Quadruped, developed by Gary
Lvov.
Oh, sorry about that, Lvov.
Don't worry about it. All right, I'm going to share my screen here. Let me know if you can see everything.
Yep.
All right, so I built a quadruped as part of an independent study in my senior year of high school, and I built it kind of backwards. I think that a lot of people use ROS and Gazebo as tools to achieve an end goal, an end robot, whereas I kind of dreamt up this project to learn how to use ROS and Gazebo and basic robotics tools. And so Sparky is built from about $850 worth of components, and that's very deliberate. I'd love to build like a $10,000, robot, but this is a school-funded project, so I had to keep the costs relatively low as I could get them. And there are a few other limitations. My school's 3D printer was broken this year, so I had to come up with some creative design solutions how to get around that. I ended up CNC milling some of the parts, and I use mostly off of the shelf components. So I'm going to show some highlights right here, some of what Sparky can do. Here's an early version, kind of just turning, etc. Here is live visualization of joint states, and this is all done through ROS. I'm going to get into how I use ROS in this project in a little bit. Right here, we have some navigation. What's that?
Not RRS, ROS.
ROS. Sorry, and then here we have some more walking around with the robot. And so since I use ROS and Gazebo, once I got kind of them down in the context of this project, I was able to kind of crank out multiple versions in a very short period of time. And so I have some of the improvements here on the left. We have top left, we have like the first version. As you can see, that doesn't even walk properly. And then at the bottom, we have the final version. And so this is kind of a schematic of what's going on within Sparky the Quadruped. On the computer is where I had all the gate calculations. I'm going to get into what I used for gate. And basically the computer took in all of the sensor data, and then the computer computed the desired motor position and sent it over Wi-Fi to the Raspberry Pi, which sent over ROS to the OpenCM board, which sent it to the Dynamics of motors. And so I'm going to show the same schematic, but a little bit simplified and remove the power, remove some of the things. And using ROS here was very key to kind of facilitate all of this conversation. I talked about using ROS to kind of like streamline this project. And this was really key because I didn't have to write any of my own communication protocols. I was kind of able to plug and play with ROS. And on the Raspberry Pi, I was running ROS built from source. With just like a few very minimal packages. On the computer, I was running kind of like the full desktop install with the gate package I'm going to talk about in a second. So the gate package is something that I kind of found something that someone else did. There's this gate package that Juan Ameno developed called Champ. What Champ basically does is that if you put in a URDF and you input your gate parameters, Champ outputs the gate for your quadrupedal robot and your ROS navigation stack configuration. And this is a very powerful tool because like I personally don't have the mathematical know-how to develop my own gate, and this kind of helped like avoid that problem, sidestep it entirely. And so on the right here, I kind of have my workflow, and I talk about how I would draw the quadruped in Autodesk Fusion 360, and I've looked at some of the online things, but it was really more like me drawing what I think would work. And I would continue down the line, and I would convert it to the URDF from Fusion. I'd configure the gate with the champ package, and I tested in simulation. And I'd love to say that I had some sort of really genius like benchmark test, but what I was really doing was that I was looking on how it kind of walked around and kind of judging based off that, how I could amend my design. And after I kind of tweaked simulation a lot, I'd move on to real life and kind of do the same thing and kind of look at the gate and try to come up with ways I can amend my own design. And then kind of outside of the flowchart here, I have select parts to purchase and configure ROS across the systems. And I think like kind of the smart thing to do would have been to test the robot in simulation first and then purchase the parts. But because of the nature of the project, I just had to purchase the parts to begin with. That was something I found a little difficult, actually. I think the most difficult thing about this project was selecting which parts would work without the use of a 3D printer, without the use to kind of build things from scratch easily. And what I will say is that even though Gazebo and ROS are very powerful tools to kind of streamline the development of robots, they do have a little bit of a learning curve, and that's what I show here on the right. Like the first like 30 Gazebo simulations I tried to do with my model and the gate package, they didn't function at all, and that's where I actually received some outside help from some experts on how to troubleshoot this, and I kind of show kind of this more accurate flow chart of like you encounter a problem, you have to fix the problem. And so see here again, I kind of show how I really was able to use simulation. Here's like one of the first versions once I finally got Gazebo running properly on my machine. And as you can see, like it isn't that good. And one of the final versions, it's significant improvement. And I think that even without like very like precise tests on some level, you can kind of like eyeball it and see what's going on in Gazebo and use that to refine your design. So just to summarize, 3 tools I used that were absolutely essential to kind of make this project happen in such a short time frame were ROS, Champ, and Gazebo. And I'd like to thank a lot of people who helped me come up with this project, help this project come together. All right, thank you. I'd love to take any questions now.
Thank you so much, Gary. So I think the first question that I would like to ask, because I actually run into this issue a lot just working in industry. A lot of times, especially when you're starting a brand new project, you have a budget first, but you haven't done part selection. You might have access to a simulator. Given that, and given what you just learned, how would you attack that?
Well, how would I attack is that I'd like design my perfect robot first. I'd design if I had like unlimited funds pretty much. And I'd throw it into the simulator and see how it performed. And I'd see kind of what torques are necessary, kind of what physical constraints are necessary for your motors and whatnot. And then I would kind of make those constraints worse and worse. I'd decrease the torque, I'd decrease the amount of needed velocity, and I'd kind of work backwards from there. And then I'd finally find like the cheapest possible part that fit like the worst possible torque, the worst possible velocity. Okay.
No, that sounds pretty good. It's I mean, there's a lot of different strategies with that, and I myself, I mean, I live a lot more on the software side of the world, so learning about how to actually go through like part selection and trying to actually engineer a problem from that direction is always something new for me to learn.
So that's what I really wish that I actually did with this project. This project, because of like the time constraints, I ended up like just going through the internet and seeing what motors had kind of pre-made brackets that I could utilize for this project. And that's why I chose the Dynamixels actually, because they had like the Bioloid brackets that I could use really easily. So that's what I wish I did in this project.
Okay. All right. Looking on the chat here, the next question is now that you've learnt ROS and built a prototype quadruped, do you have any idea what your next project might look like?
Yeah, so I've been working on a project this summer. I've been trying to learn ROS 2, and I've been trying to pick up a little bit of the reinforcement learning, like the really basic stuff. Kind of a project that I conceptualized at the beginning of the summer that maybe would have been like a little bit too ambitious is that I wanted to balance an inverted pendulum with a robot arm, using kind of like the reinforcement learning for the balance, and maybe something like move it for the control of the robot arm. But I have to be honest, like reinforcement learning has had like a really steep learning curve for me, so that's something I've been struggling with.
Understandable. I remember my days learning that too. So
yeah, it's like way over my head. Like
I promise you, at some point you're gonna have an aha moment, and then you're gonna wonder why I wasn't clear for you earlier. But I think that's true for everyone.
Just like Roz, you'll have the same thing that eventually it will click. And I've not done RL yet. I'm just a believer that, you know, eventually you'll have click the same learning curve.
Mm-hmm. Right.
Sorry, I just want to chip in real quick. I remember originally when you put in your application, you said it was done, you know, this was a 3-month project. So it's nice to see that you continue to develop it over the last couple of months, and it's come a long way since then, which is really nice to see that you're continuing to work on it.
Yes, so pretty much the only time constraint I had is that I had finals at the end of the year. So I was kind of like gunning for as much progress as I physically could before I kind of had to study.
Sure. Okay, John, back to you.
No, actually, I was hoping you'd have a few more questions. We are running a little early right now, and could fill in a little bit.
Okay, I can happily put up a couple more. Do you mind going back a few in your slides?
Sure.
So I can get another look at it. So yeah, it's impressive how much work you've got into it. So it's using the LiDAR then.
Yeah.
You've got autonomous move. It's mapping then, and you can then set it from one location to another.
Yeah, so that's using the navigation stack configuration generated by the Champ package.
Yeah, absolutely.
Something that isn't perfect with this project actually is that the motors, they have a lot of slop in them, and so the localization isn't perfect.
Sorry, what in them?
They have a lot of play. Like when the motors are fully engaged, backlash, yeah. They have a lot of backlash in them. So I found that the localization in the gate was actually like pretty flawed, because in the model it's perfect. There's no backlash, so that's why you see it like drifting here a little bit.
I also see the LiDARs constantly moving around, and that I can't imagine that's helping. Doesn't seem to be affecting it too badly, but I can't imagine that's helping. And there's not an IMU or any attempted internal localization either. So you're relying on one sensor, and it's doing well considering. But LiDAR is very powerful in these small constrained environments.
So I had an IMU, but I didn't have time to implement it. I played around with using scan matching from the LiDAR, but I found that since the platform wobbles a lot, the scan matching wasn't accurate either.
Yeah, you're not going to be able to do better than what they've got out of the box for that.
That's also one of the weaknesses you'll get out of just a single line scan LiDAR as well. Just because you can't really tell where that plane is exactly hitting. Even if you stack 2 or even 3 of them on top, you'd probably be able to power through that. So
you could consider buying a cheap camera gimbal off eBay, putting it on that and seeing if you can get it to stabilize. That could be a fun weekend if you have the money and the time and the ambition for it. That's your own call, not mine. It's easy to have these ideas when you don't have to commit to them. So you're saying then, look, moving to ROS 2, how would you say your experience has been thus far transitioning from ROS to ROS 2?
I really like ROS 2. I kind of like the struggle that I had from ROS 2 is that like I didn't have a lot of experience with object-oriented programming. And in ROS 1, you can kind of get around that. You don't really need to kind of use objects at all. You can throw everything in the main and kind of hope for the best. And so for me, like learning how to use the object-oriented stuff with ROS 2 and the RCLC C++ core, I think it's called, was really rewarding. And it was nice to see code that didn't just use a ton of global variables and whatnot.
Okay. We got one more question actually that just popped up online. I think this one is not really a next steps, but a longer term sort of thing. So going farther out, what kinds of robotics projects would you like to work on?
So I haven't really narrowed that down yet. So I'm going to college this fall for mechanical engineering, but I do really like the software side. I wish there was kind of like a pure robotics major. I'm going to figure that out as I kind of go along. Like I like what I'm doing now, and I really like building like the whole robot is what I will say.
There are pure robotics majors, but if you are transferring into a robotics at a master's level after doing a degree in mechanical engineering, you'll be very well placed. especially if you've kept up in the way that you are already prepared with ROS 2, you'll be fantastic when you transition into robotics at a later stage with a degree of mechanical engineering under your belt. So this can work out for you in the long run. Don't worry.
Thank you.
Yeah. All right. Well, we are still a few minutes early, but I think we can probably safely transition to our next topic. So Hank Shaw will be presenting damage recovery for Hexapod robots.
Yes. Yeah, I'm ready to start anytime.
Thanks, Hank.
So, do I start presenting now?
Oh, yes, please.
All right. Sorry, can you see my screen?
Yes, we can.
So, all right. So, so my title is Damage Recovery for Hexapod Robots. I'm more going to be presenting in a story kind of way. So, just to give you a bit of an introduction, this is my Hexapod robot. I'm not someone with a very strong background in robotics. I basically pieced this up all by myself, by self-learning through online. So right here we have on the left is a modular robot called Miro. So I kind of won this on an online on a competition in my country, Malaysia. So I've been using it for 6 years in a row now. So it's kind of worn off, but it still works for me. So right here in the interior, we have ESP32, a motor driver for providing powers to all three other boards. We'll be explaining how all these other three boards will be working later. So here we have a G15 shield, which is responsible for controlling the motors individually at, so there's like 3 motors for each leg. So there's like 18 motors in total. And the Arduino Mega is basically the one who will be giving commands to the shield. The ESP32 there is just for Wi-Fi communications from a PC for processing capabilities. So when I started this project, basically I was just having fun exploring nature's inspired robotics. So I always like to build robots like snakes, praying mantis, anything I can find on in the wild and just build robots. So here's a basic locomotion. So as you can see, it's basically, there's no special inverse kinematics at all. I basically programmed each motor one by one. So it took me quite a long time, about like 1 month just to get it right, because back then I literally had no official training in robotics. So the way I approached this was 3 legs will be lifted out at one point and the other one will be touching the ground and they'll be switching occasionally. So I referenced this from ants. I would like slow down videos of ants moving online in YouTube videos and try to reference them. So moving on to the next one. So I decided to add an object tracking feature using Wolfie, which is a C# programming with Unity. It's an augmented reality application where you can track an object and you can draw a bounding box. And that gives you a code, like the coordinate of where it is in the image. So it's not something very fancy. It's just basically if the bounding box is too much to the left, it tells the robot to move to the left. And how it does this is basically the smartphone is connected through the ESP32 with a Wi-Fi hotspot, and it's just sending, oh, turn left, turn right, images on the right, etc. So it's something like that. Then I was thinking, like, is that all it? Like, you know, like, how do I push it forward? So I was studying at the University of Southampton, and I noticed this paper in Nature, and they have this thing called MapElite's algorithm. So it's actually an algorithm where you basically, instead of training lots of data, we call big data, we have this thing new called microdata, where you use as least data as possible to train a model that allows robots to adapt to damage. I was like, wow, okay, this sounds cool. And turns out one of the lecturers was in my university study. So I was like, why not take this as my 3rd year project then? So I proposed the idea to my lecturer, and my lecturer was happy about it, and we started working on it for my entire year. So just to give you an example of the motivation. So basically, the algorithm is to solve the problem of pre-designed contingency plans being limited by the variable creator. So you can't foresee every incident there is because you are human and humans make mistakes. Reinforcement learning methods could be used as an alternative, but the process is slow because of simulation and processing power, and I don't have that much of a budget. So the goal is to use a method that allows the robot to adapt the damage in the environment under limited number of trials. So I'll break one leg of the robot, it has to adapt to a new method of walking in under less than 20 trials. So first things first was that I will create a model of the Hexapod robot using Fusion 360. There'll be there's a 3D model of it, and I upload it to ROS, and it will output a URDF file. And using this, we'll input it into a map-release algorithm, which basically is like your typical genetic algorithm. So basically what it does is it populates, it tries one style, then if it's performing the best out of like 10,000 robots in the simulation, a seed of it is selected and it propagates forward, like how animals reproduce into an evolutionary theorem. So then here comes the magic part. Out of 10,000 solutions, let's say 10,000 solutions, you've generated this huge model. You have 10,000 solutions of different ways of walking, etc., jumping or leaping and stuff. How do you select the best way to walk in such a short time? You only have 20 trials. Let's say each trial is 5 seconds. You have to adapt in like less than 1 minute or 2. So we have this thing called Bayesian optimization. So it's basically an algorithm where you try to model a probability distribution of the entire model of which solution is the best solution for this condition. So let's say if the robot chooses a leaping condition, I'll jump and I'll record how far I've walked. And basically, this is the magic part. It only takes in how far it has walked. It has no other sensors, no camera, no torque behavior, nothing. Just how far it walked. It can model which next solution is a better solution. And it keeps improving the model and finally selects the best one. So all these solutions are sent into the robot and the robot keeps reevaluating the performance. So here I've recorded a demo with my own voice. Hope you don't mind it.
We're currently hearing no voice from you.
Oh, sorry?
Yeah. Your audio's just gotten very quiet.
Oh, the video is not playing video. It's not playing a sound, is it?
No, your whole audio has just gotten very quiet, including your voice.
Oh. If that's the case, I will just share.
Anyone else hearing that? Okay.
I can hear him. I can't hear the
video, right?
The video.
Yeah. Okay.
There should be an option video then. To share your audio.
You can hear your voice fine now.
All right. If that's the case, I actually have I'll just share the direct video then, if that's fine.
Okay, that's wonderful. And people can watch it.
Yeah.
In their own time.
Can you see the video?
Yep.
Yeah, and you can talk us through it.
Oh, there's supposed to be audio in the video as well. I'm not sure if you can hear.
That's okay. You can just tell us about it.
Yeah. All right. So basically, right here is you have 3 different damage conditions. This one is basically the base model, 1 leg removed and the other leg removed. So, hold on. Yeah, just move forward. So here right now is basically, there's 30 centimeters for each tape, and you can basically see how far moved every trial. So the robot only gets how far it is moved. I literally did not give any other sensor values, no torque, no current. So for the base model, because it's a different environment compared to the simulation environment, I give it 10 trials to see if we can find anything special. And the other one, I give it 20 trials because it has basically a damaged leg. So I expect it to take a longer time to adapt. So you can see that every time it tries, it's always trying a different way of walking. Sometimes a bit jumping around. And this one is, so this is kind of like the final way of walking. So just replaying the best gates. You can see it's kind of like moving, it's like sliding to the left, kind of like walking like a crab. And this is another experiment I conducted by removing another leg. So this is like just a very typical standard style of damage condition. And this is like a crab-like movement. This is basically just random solutions I selected in my model. And this is more like a leaping movement. Right. I'll continue sharing my presentation. So one thing I want to point out is the challenges in building project. So number one, I've already said it was the cost. A lot of the things I couldn't have my access on because of the COVID-19. So basically, I tried to access my university's lab, but the pandemic was pretty bad given the time. So I had no access to the soldering. So you can see that my wirings are pretty bad. There's like no wire protection at all. So sometimes things just fall apart, etc. And I basically had to learn RRS on the way during the execution of my project, etc. Yeah. So that's about it. That's about it for my project. So any questions? Just go ahead.
Thank you so much. So I think the first question that I kind of want to ask about is, because you were able to show two damage conditions and basically how the system was able to learn to overcome that.
Yes.
That said, I mean, I'm sure there comes a point of no return. Have you tried investigating that sort of direction, or is there anything I would even say like a stop limit to, you know, after so much being damaged on it, we're not even going to attempt to do anything to complete the mission?
Well, the fun thing about this algorithm is that you can do your own soft limit, but this algorithm is quite, I would say it's versatile. So basically it doesn't only work for hexapod robots, because basically as long as you can create an evolutionary generation out of a robotics model, there should be a solution for every problem. But of course, we're talking about idealistic conditions here. I would say a hard limit would be like 3 legs, because I tested out with 2 and 1 legs, and they all still seem to do up to recoveries like 50% of their performance. But 3 legs above, they just stop. They're just trying out random stuff and can't move anymore. Yeah, I don't see a significant performance, but I would say that it varies for different models of the robot, definitely. Yeah.
Okay. Yeah, I mean, I can imagine a certain point where it's like if there was only one limb that was still working, kind of limping along.
Yeah, it does try that. It does try that, but it's very slow.
Yeah.
Yeah.
I can ask, and forgive me if I missed this in the presentation, but were you applying this just to the whole limb stopping working, or were you applying this to, say, the joints gradually wearing down over time?
Sorry, I don't understand.
So are you saying you're trying to run something that adapts as the robot gets damaged, right?
Yes.
And you have 6 legs, and so you're saying 1 leg gets taken out of the equation.
Yes.
What would happen were you trying to simulate a tool, say, one of the motors only starts working at 50% performance, for example?
Yes, that's a very good
Would
question.
you like to simulate that?
Yes, that's a very good question, because the interesting about this algorithm is that it only takes in the distance it has traveled. So if it notices a drop in the performance, it just starts adapting immediately. It doesn't know if its motor's legs are broken at all. So in the experiments I've shown just now, it doesn't know one of its legs is gone. So it's like it's adapting just because its performance has dropped, not because its legs is removed.
So then maybe you could potentially use this on a two-legged robot, not to have it work for when the whole limb is damaged, but to help out for the fact that a robot in the real world is going to have motor wear over time.
Yes.
And you can't predict that for every single robot. So having something like this that can evolve with the robot and keep it optimized works fantastic.
Exactly.
That's really interesting. So we do have a question online. It is, can you explain the way you've set up your evolution for the Hexapod and what it might look like for other robots?
All right. So I kind of have a slide hiding over here. So I think it's, because I was worried that this might be a bit too confusing. So basically, this is basically how the behavior performance map look like. So basically what I'm doing right here is I'm plotting how each solution's performance look like by default where no legs are removed. So here you can see that each leg is measured as D1, D2, etc. And what I did was I created a 3D model of the robot, and I will load it online called the algorithms called MapBelids. You can search it up on GitHub called MapBelids. There's basically a whole README file on how to set it up yourself. It was so useful for me. I basically just followed through the README and I had my first model out in no time. Yeah. So once your model is output, it should look something like this. So basically what this shows is basically you can say like it's a graph in a graph in a graph. So for the first two legs, you have this plot, and then for each point, you have a smaller graph, and then you have another smaller graph for each small box. So here you can basically say like for the duty cycle, for 0, 0, 0, 0, so 6 zeros, means that the robot is touching the ground, it's lifted up on the ground all the time. You can obviously see that there's no solutions generated. But you can see that in the center, where it's like 0.6, 0.5, where the robot's like kind of like just switching around. You can see that it's very high performing. So one thing I want to point out is that the interesting thing is that let's say D1 is removed, all right? So the robot, even though he doesn't know D1 is removed, he'll actually eventually find a plot in the graph where D1 is 0. So let's say if D1 is 0, which we have on this graph here. So you try to look for solutions that are along this line that has a high behavior performance. And of course, the map, which is you see the red, the green, and the yellow, it changes every time update. So you can see the red line, the red plot starts to shift to the left. Yeah. So it's kind of something like that. But I can't explain everything in 3 minutes, obviously. So I would say the best way to start understanding how the algorithm works is actually to look up on the README file in the MapBelids algorithm. Just search it up. It's really, really very well documented. Trust me.
Okay, I'll ask you to share those links because we're going to post after the fact a big Reddit post with all of the links in it for people who have asked about them during these presentations.
All right.
Yeah. So I do want to ask one final question. And it's because it's actually something I didn't even think of myself, too. A lot of us tend to think about, yes, the thing gets damaged, how do we recover from that? How do we move forward? Well, what if we go the other direction? Suppose we add another limb to it. We add more capability. Does the algorithm work in the other direction?
Sadly, it does not. So basically, the model is trained on maximum number of legs. Mm-hmm. Yeah, so it doesn't quite understand that if there's a new leg added, because there's basically no signal coming out of the robot. Yeah.
Okay. No, I figured as much, but I figured if maybe it was like a infinite input control. So, I have seen my share of those too. So
wow. Yeah.
Yeah. Awesome. Well, thank you so much.
All right. Thank you.
All right. So now it's time for our final presentation. Jeff Underley will be presenting a quadruped with 3D printed recirculating ball screws.
All right, can you see me? Can you hear me?
Yes, I can.
All right, thank you guys for having me. Let me share my screen here. All right, so it's really cool to be a part of the show. I'm really appreciative, and I'm a mechanical engineer, so robotics isn't typically what I do, but this is more of my hobby and passion, getting more into software engineering. So I try to build projects that push my limits and give me a roadmap of different things that I have to try to accomplish. So built a quadruped using DC motors and ball screws, initially inspired by James Bruton's YouTube Open Dog series. He had a really cool series where he rationalized a few key concepts and really just started getting my gears turning and making this project feasible for me. So I had a couple of goals with this. One, give myself a platform of some kind of robotics platform to learn embedded engineering, embedded software, different microcontrollers, different subsystems, going through and testing those subsystems and getting those subsystems to interact with each other and interface properly. The second part of that was to give myself as much as I possibly can, but while also keeping the cost down. Brushless DC motors are great. They're ideal in this scenario, but the controllers and the drivers weren't really feasible for my budget for this project. So I decided to use DC motors, and I tried a few different variants. So originally I wanted to try cycloidal boxes and different approaches with high RPM DC motors with high reduction. And I just wasn't really finding a happy medium there, just buying cheap motors with no documentation, testing them and trying to find just a sweet spot. And ultimately I landed with a gear motor bought off eBay for about $9, and then started going down the road of developing a 3D printed recirculating ball screw. So a ball screw takes ball bearings and a helical pattern and then channel them back start to finish so the bearings can function continuously while translating rotational moments into linear force. So I went through several iterations. I've got a box full of just old parts and different things like that. And to really maintain that, minimize the cost, I challenged myself to 3D print anything that I could, or really just push the limits. So bearing races are printed. I even have that T5 timing belt printed out of Flex PLA. It's surprisingly flexible with a whole lot of stretch. So it works really well. Just kind of shrink it down a little bit and reduce the center and it produces a pretty good timing belt. Ultimately needing to print 12 actuators, I decided to use my SLA printer for the ball nut. And it was printed in this transparent material. And so it really kind of gives a great visualization of what's happening here with that. So hopefully this video loads and isn't too choppy for you guys. You can actually see the bearing balls rotating around in that helix and then being fed from start to finish. Almost. Give it a couple more seconds before we give up. There we go. So there, I'm just holding the ball nuts stationary and rotating the screw. In application, the screw itself is held stationary and not allowed to rotate while the ball nut rotates around it. So a pretty good example of that action. So I had 12 of those. I got printing and assembling. There's a lot of hours in that, and there's a lot of questioning my choices on printing these bearings and assembling the 1/8" balls by hand. There's about 1,100 1/8" ball bearings in this assembly. So that was time consuming to build. Knowing that 3D prints have pretty good strength in X and Y, but poor Z layer adhesion. I do have a threaded rod that passes through the ball screw itself. So There's really minimal hardware used within these ball screws, but that really allows us to have that tensile strength requirement for different positions and forces. And they actually turned out to be very robust and quite strong. I was able to test the gear motor's torque with a rudimentary setup with a scale, but I just don't have the equipment to test the actual strength of these actuators. I can't stop them by hand. So I was pretty happy with those performances. They do each have a min and max limit within the assembly. I do have all the CAD open online, so people can open up the Autodesk Share or open up a step file. My original thought had a mechanical encoder geared to the ball nut, but ultimately that didn't really work. I was just getting too much V-bounce and I couldn't filter it with hardware or software. So I gave up on that and I went to the magnetic position sensors. It offered me another subsystem to test and integrate. So I was pretty excited about that. With the actual frame, it is again fully 3D printed, utilizing that XY strength, keeping parts flat on the bed to minimize their print time, and then using a interlock, almost like a puzzle. Everything kind of locks together. The hardware pins it all together, so the prints themselves take pretty much most of the load. The hardware just clamps the surfaces together, and it gives a pretty robust and pretty stiff frame, considering that it's about 30 hours of print time for the individual components. All the bearings are 1/8 inch balls except for the shoulder joints, which are 6 millimeter airsoft BBs. So again, pretty cheap off the shelf component, several thousand BBs for a few bucks. And it produces a pretty nice, robust shoulder joint for those higher shoulder loads. So capturing that high moment load within the frame and just keeping everything rigid and then transferring that load from front to back as you lift up one leg. The legs themselves were probably one of the bigger challenges that kind of shelved the project for about a year. I had originally designed one leg that was just too flimsy, just put it in the back of my mind. And then one day I kind of came up with this other idea of, again, printing flat and actually design these in Autodesk as a sheet metal component. So not to have the misnomer of, are they sheet metal? They're just designed in a sheet metal form. So it's a angled piece, flattened out and printed flat, and then using a heat gun, heat up this relieved joint, bend the plastic part into position, and then set it all into place. It cools and then becomes rigid, and I get this nice triangular shape, a lot of section, and more than enough rigidity for the legs. So was able to carry that design concept through the upper and lower leg joints. To minimize space, all the bearing races are printed directly into the pieces. And again, just popping in those bearing balls to just minimize the having to put a bearing in it and then wrapping plastic around that and just having more interfaces and weakening the joint of the plastic. The control side, that was the learning experience. That's what I really wanted to push myself in. So it is a little bit of a complex network, using an ESP8266 as that central Wi-Fi enabled main processor. And then they're talking to a couple of STM32s, which handle the front and rear IO respectively. Then going down to their DC motor drivers. It's a TN6612 FNG DC driver. I'm using both channels of those just to accommodate the current requirements for these motors. But everything has been working out really well. Everything kind of fits excessively snug into the frame. It was definitely some long hours there trying to solder everything and again, questioned some life choices there. But eventually got everything together, troubleshooted the wiring, and this turned out pretty solid. Like I mentioned, I'm using the AS5600 angle position sensor, magnetic angle position sensor. And it offers me to be able to directly monitor those joint positions. Originally, I was using encoders with the mindset of pulling out the encoder on startup because it was an incremental encoder, not an absolute. It would lose position and wouldn't know where it was. So I was really excited about that accidental change. It added a little bit of work, but offered another subsystem to test. The network itself is driven by a phone app. So I looked at several different apps, and I found Blink, and it offered amazing customization, was very easy to implement. I think I had it up and running that evening. So I was like, this is the way I'm going. I can send control signals to it in real time. I can change parameters. So I'm passing about, I think, 20 control signals to the robot to adjust speed, foot height lift, PID parameters, different things like that. I am running it on a local Linux Blink server, which isn't required. The app itself does run through the cloud, but to minimize latency, I am running on that local server. It goes and talks to the main MCU, the ESP8266. That does all of the inverse kinematics, does all the calculations, and basically sends out all the set points. So the ESP and the STMs are on a I2C bus. Basically, the firmware for the front and rear STM32s are identical other than their I2C bus channel or address. The ESP sends the batch of 6 joint set points to the front, then sends it to the back, then asks for the front measurements, asks for the back measurements, and that heartbeat happens with an adjustable frequency. I'm running, I believe, 50 hertz right now. The STMs just sit there and wait for that request, send, receive command, and once that's all done, then they do all of their PID calculations, sending out signals to the DC drivers, reading the AMS 5600s. One of the interesting things about those AMS AS5600 magnet position sensors is they are fixed I2C addresses. Kind of one of the big things people are like, don't use them. They're difficult if you want to use more than one.
Just
liking the challenge.
You've got about 2 minutes.
This is my last slide.
Okay, cool.
Thank you.
Yep.
So I utilize those multiplexers to read all those position sensors, and some of my cables are 600 millimeters long. So going through and trying to isolate those channels was a good challenge, but overall, it definitely achieved my primary goal of giving me a platform to really push my knowledge in a lot of these subsystems that I don't really have the discipline to. This is just a passion of mine. And going forward, I definitely want to implement other higher control systems. Watching this whole robotics showcase has definitely got me thinking about other things and different systems that are available. Definitely want to learn how to use those in simulation. I do have it. Let me end my share here so I can go back to my full screen. I don't know if you guys can see my full screen.
Right now we have your camera.
All right, so you guys can see it. Let me let me try to move it in position. So I did write the walk algorithms by hand. It's wonky. There are issues that I definitely want to progress and work through. But if we enable it, and we can set the parameters. So just demonstrating the translation methods, it moves pretty smooth within translation, and I can do XYZ translation with a yaw movement. I omitted pitch and roll just because it did complex the math there, and not using simulation software, it just was getting to the realm last, spending too much time on that. And then the walking mechanics it's a little wonky, but it does move leg at a time, and it's trying to move the feet that are touching the ground. And then it picks one leg, picks it up, moves it down. And so it is able to technically walk. So
interesting.
Wonky walking gait or not, you successfully gave a live demonstration of a legged robot.
Yeah.
The keynote speech.
That was the goal.
Okay, that's an incredible achievement. We've only,
last night was touch and go, and I was charging batteries this morning. So
and we have had a few that have gone wrong because it's perfectly normal for them to go wrong when the cameras are on. So well done.
Thank you.
Are you part of the quadruped group that Piotrek and Robin are part of from the other two quadrupeds?
I am not.
Then I'm sure that there will be someone who will reach out to you. I'm not a part of it because I don't build quadrupeds, but someone will get in touch with you about that. There's a community for you who will help you with this robot.
By all means, all of this is posted online, Thingiverse and Hackaday under my my handle as Design Cell. So step files, AutoCAD files, pretty much open to it. All the firmware that I've done with it. If someone wants the challenge of building this, overall, this is about $400 build.
Nice. So that said, actually, and I think this is a really good segue into our first question. Materials and material cost is one thing. How much time did you actually put into just trying to figure out, like through trial and error, like some of the tolerances you had with your designs?
So, yeah, this has been over probably 2 years. Originally watching that Open Dog series, I pretty much right away started developing the ball screw actuator. And I created different variants and different sizes and travel lengths, all around the same geometry design of the belt drive to the 4.5 pitch millimeter screw. So they're all about 20 millimeters, and design different variants. And then I was just like, okay, now I need to start looking at the robot. Time-wise, hundreds of hours.
Wow. That is impressive. I mean, like it's obvious just looking at it, like just how much time and effort you've put into it. I mean, it's extraordinarily impressive. I mean, I could tell you and agree with Ollie entirely. Like,
so when I saw the application, I thought the ball screws were partly 3D printed, as in part of the casing would be 3D printed and the main mechanism would be parts. The whole robot is 3D printed. It's incredible.
To the best of my ability, I 3D printed as much as possible.
Yeah, that said, obviously, there are pros and cons to doing this. And when you're finished with this project and you then move on to your next project, do you think that you would continue to go down that route, or you would want to then investigate using different materials and different construction methods?
I'm a mechanical engineer, so by profession, these are components that I'm familiar with using. Ball screws, linear ways, and servos within industrial equipment, hydraulics. Those are things that I do from day to day. This is a home project. I don't have a corporate or school budget. So it's really just, what can I do with the resources I have? And unfortunately, I have to buy a motor.
No. So, and this is only meant as praise here, and we can get in touch and talk about it afterwards. But aluminium extrusion is a very common tool that robotics engineers use for putting together these kinds of robots cheaply, for taking a lot of the kind of the core weight and the stress of it. That can often be something huge. John, I don't know if you want to chip in at all.
Yeah, I mean, I'm sure you can probably see my Ender 3 sitting over my shoulder over there. So I feel your pains entirely about 3D printing parts, because that's what I can afford to do. I don't have a school or a corporate budget, even though I work for a robotics company. That said, though, I actually do want to touch on maybe another thing with this. One of the other questions that we have online is, do you plan on expanding and making like proper PCB boards instead of just using like the prototype boards that you were using through your electronics?
Absolutely. Soldering all those wire connections and connecting everything really made me question why I didn't just take the plunge and learn how to do that initially. Several of my clients are PCB manufacturers, and so I have those resources to learn those tools, and then like PCB Way or different resources online that just make hobbyist PCBs really easy. definitely made me question why I just didn't do that from the beginning. But it's just like, well, I had these pieces. I'm just going to do it and go, well, learn what I can from it, and then in the future, definitely plan around having those fabricated. Absolutely.
So let's see here. I mean, I actually have to admit, just looking online, there is just a ton of praise actually for all of it. One comment even saying, you know, $400 for just making this is ridiculously awesome, because a lot of times that's just the cost of a single actuator.
Right, that's what blows my mind.
I'm working on a robot that uses motors that are around about $500 per. Yeah, you know, the high-end Dynamixels, they're setting you back hundreds of dollars per motor. So again, to be able to build all this for that kind of money is incredible.
Mm-hmm. Yeah, I do have a full bill of materials posted to those resources. So it should have quantities of hardware and different things like that. And a lot of these components were bought in larger quantities. So it's around $320, I think like $20 per actuator, and about 4 to 6 kilograms of material. So.
Mm-hmm. So if I could ask, and this is kind of a slightly off-topic question, but not quite, what is your day job then? Since you say you are a mechanical engineer by profession, and you regularly work with like linear actuators and things like that.
So for about 8 years, I was in industrial equipment design doing automated reclaim storage systems. Reclaim systems at the bottom of large storage bins, sometimes hundreds of feet in diameter, producing just tens of thousands of pounds, weldments and hydraulic and electric equipment with PLC automation and different things like that. More recently, because of the birth of my children, I have taken a step back and just doing a consultant engineering work, supporting clients with 3D design, supporting electrical engineers with enclosure designs and 3D printing prototyping. So still just kind of keeping into that mechanical engineer, mechanical design engineer, but more so moving, I do have the vision of moving my career to software engineer.
Cool. And also congratulations on the children too.
Thank you.
That said, we do have a couple new questions that popped up on the chat as well. Can you talk about the inspiration for that bent 3D print technique that you had?
Yes. We needed a drying rack for dozens of bottles because we actually had twins. So we were going through about 20, 24 bottles a day. So my wife asked me for a dual level drying rack, and I just came up with this design where I flat printed a riser and then heated up the seam and folded it and pieced it together within that drying rack. And that just like, oh, I could use this on the legs to stiffen the geometry, and then it just snowballed this project right back up again. So yeah, absolutely.
Awesome. All right, I think this will be our last question for the night. So the question is what did you use to actually run the bot itself? Are you using a Nano/NX?
No, this is all written in firmware.
Okay, interesting.
Yeah, all the inverse kinematics is written in firmware within ESP8266. It does all the calculations. Basically, the way it functions is it receives the joystick input from the Blink app. So we have XY translation and then yaw translation. It sees that within its loop cycle and then adds that portion of the joystick. So if you're at full joystick, you're getting that full additive millimeters per second added to the XY translation.
Awesome. Well, thank you so much again. So
thank you.
All right. Ollie, you want to close us out?
Yes. Right. Okay, then. Jeff, thank you very much. Fantastic live demo, fantastic robot to end on. But really, just about every project I think we've had today and yesterday have been absolutely fantastic. It's been wonderful to see such a wide variety of projects coming from people of all ages and abilities, which is what we set out to achieve. And so many projects that are succeeding in what they're trying to do. Not just, ambitious but a bit rubbish, but ambitious and a bit successful, really. And so many of these guys are really pushing themselves. When I say guys, though, that does take us on to the one thing that we've seen as a negative of this year was we originally kept our application process anonymous because we wanted to protect users' privacy from Reddit. It was only when we were putting together the website, which took longer than we envisioned, we saw at the end that with one exception, we have an entirely male cast. So our main goal for the coming year for Reddit is going to be trying to look at improving our gender diversity. You'll be able to hear more about this over the coming weeks as we will be putting out a call for women to join the moderation team. And we're going to be, over time, I've talked with the people we promoted this event with and have received a lot of support and a great list of resources and people who are willing to talk with us. And so we will have a lot to feed back on, and hopefully we'll be able to get a lot of really experienced women in robotics at different areas of the world who can talk about their experiences and their projects and their work, which we're really excited for. This has been a fantastic event. We envisioned originally 5 to 10 people and one mildly interesting speaker. Instead, we've had 4 fantastic keynote speakers, a 2-day event, and nearly 30 participants, and it's been wonderful. We've even had, 5, 6, maybe 7 live demonstrations, which I was not prepared for. And a lot of these robots have really been wowing me. Not something I expected, honestly, when I came into this. I thought I was going to be seeing more amateur work that was cute, but honestly, a lot of what I've seen has been absolutely mind-blowing, frankly. So this has been a fantastic event, and I've been thrilled to be a part of it. I know that the rest of the showcase committee have too, and I'm sure that you watching as well have. Any other committee members want to chip in with anything before we close off?
Yeah, I would love to say thank you, Ollie. Like, we have all worked really hard, but this would not have happened without you constantly pushing and organizing and reaching out to people. And just this whole thing has been driven by you, and we're all grateful for the leadership that you've shown.
Oh, well, I do appreciate that. It would not have been successful had I done it all myself, and I would not have done it. I would have given up about a week in if it had just been me. So this has been a team effort, certainly. And so I think next year as well, we've got a long list of things that we want to do better, and I'm sure we'll be adding a few more people to the team, including, again, some women to the Showcase Committee panel next year. But with that said, this has been a fantastic event. We're so thrilled that it's run smoothly and it's all gone well in the end. We were quite nervous in the week running up to it. We hope you've enjoyed it and learned from it and are more excited and motivated to go back to your own robotics projects. And we hope that you'll consider participating next year. So thank you wherever you are in the world. Good afternoon and good night.